afternoon, everyone. This is Heather Ward with NBPHE, and we're going to be starting the Biostatistics Review Session webinar in just a moment. I wanted to let you know that Dr. Sullivan will be taking questions along the way, so if anything comes to mind, please feel free to type your question into the box that you see on your screen, and we'll be taking breaks throughout the webinar to answer those questions. At this time, I'm going to turn the webinar over to Dr. Lisa Sullivan.
Okay, thank you. Welcome, everybody. My name is Lisa Sullivan. I'm the Associate Dean for Education and Professor and Chair of the Department of Biostatistics at the Boston University School of Public Health. I've been teaching intro biostatistics for lots of years here at the School of Public Health, and so my goals today are to review the core areas and answer any questions that you might have in preparation for the exam. So as Heather said, please feel free to write your questions in the box, and what I'll do is stop where there are natural breaks as we shift from one topic to another, and certainly as I see questions piling up on something that doesn't appear to be clear, I will take a break and try to address those before we go on. So please do post questions. This is funny sometimes. You can't see each other's faces, so I won't know if you're really with me or not. So you'll have to post your questions, and I will try to get to all of them as we go through. I have a set of slides here that will be available on the National Board of Public Health Examiners website, and there's also a chapter under study resources that you might find useful that has more text to it. Get rid of that. Okay, so let me begin. What I want to do is cover two areas of biostatistics, descriptive statistics and inferential statistics. With descriptive statistics, what we try to do is summarize a sample that we select from a population, and there are lots of tools and techniques that we use to summarize information. I'll walk through some of those with you. And then really the application of statistics is what we call inferential statistics. This is the power of statistics where we make inferences about a larger population based on what we're seeing in a sample. Anytime we do an analysis, we measure things, we collect data, and it's really important to correctly classify the variables or the data that we're analyzing, because as you'll see as we go through, there are specific procedures that are applied depending on the nature or the type of variable that you're analyzing. And so it's really important when you do an analysis to look at the variables and correctly classify them, as the procedures that you use will follow from that. And so there are really three main categories. What we call dichotomous variables, sometimes they're called indicator variables. These are variables that have two possible levels. And we see lots of these in public health. Does a person have a disease? Yes, no. Does a person develop disease? Yes, no. Was a person exposed to something? Yes, no. So there are lots of variables that we deal with that are considered dichotomous, and the way we analyze them will follow a certain approach. Then when you get to more than two possible categories, we have ordinal and categorical variables. These have more than two responses. Ordinal variables have more than two responses, but the response categories are ordered. So sometimes we talk about patients being diagnosed with cancer, and the severity of the disease might be classified as stage 1, stage 2, stage 3, stage 4. So there are four possible categories that patients might fall into, and there's definitely an ordering to them. A categorical variable, again, has more than two possible categories, but there's no ordering. The responses aren't higher or lower. So an example that we use a lot, is race ethnicity. We're often interested in health disparities, and we might compare people of different race ethnicities and classify them into those different categories, and there's no ordering whatsoever. And then we have continuous variables. Continuous variables, sometimes they're called measurement or quantitative variables, And these assume, in theory, any value between a minimum and a maximum. So examples might be systolic blood pressure, height, weight, things like that, where a person can have a value anywhere in between some lower and upper value. The next slide, I just want to set this up. Throughout this presentation, just so it's going to be a lot of me talking, but just to break it up a tiny bit, I've interspersed a number of questions, and I'll just give you a second to read these questions and think about where you would respond, just so that I hope that it engages you a little bit. If we were sitting together in a room, we might talk through the responses, but I'll just walk through them with you. So here's a question. We want to study whether individuals over 45 years are at greater risk of diabetes than those younger than 45. What kind of variable is age in this setting? Okay. And a lot of you are responding in the questions box. That's fine. I can watch that. But I'll just indicate the response here. Trying to with my clickers. Okay. Maybe it's not going to come up. Okay. There it goes. Sorry, I was hitting the wrong thing. It's a dichotomous variable because there are two categories. Now, some of you are saying continuous, and you might be thinking of age as it's measured in years would be continuous. But if in your analysis you're classifying people as either over 45 versus less than 45, and we should have 45 in there somewhere, say 45 and older, that would be dichotomous. Okay? Suppose we're interested in looking at disparities in infant morbidity by race ethnicity. What kind of variable is race ethnicity? Okay, good. A number of you are responding, and I hope the rest of you are thinking about this is categorical. So race ethnicity would have more than two categories, and there's no ordering to them. Now we could discuss how many categories are there to represent all of the different race ethnicities, and that could take up our entire time. Lots of times, as I suspect you've seen, you fill out a survey, and it asks you which of these best describes your race ethnicity, and then it may list a handful of options, and then there's often an other category. And so that sort of covers other bases that might not be covered in what's explicitly labeled. But the response here is categorical. So in statistics, what we want to do is when we have information, we have to summarize that information. And so there are both numerical summaries and graphical summaries. Both are important. Some people are more visual, some people are less visual. So when we often summarize data, we'll put together two different presentations to be sure that all of the readers understand what it is we're trying to summarize. So this particular table that you see here, and I'll walk through it, is what's called a frequency distribution table. And in this example, what we're measuring is individuals' health status. And you may yourself have completed a survey. Sometimes you're sitting in the doctor's office waiting to go in, and they have you fill out a questionnaire, and they'll ask you, how would you rate your own health status? And they give you a variable, a question on the questionnaire, and your choices are excellent, very good, good, fair, poor. And so this would be an example of an ordinal variable because there are 5 different response options. So respondents have to choose from one of 5 options, and there's definitely an ordering to them. Excellent is better than very good is better than good, and so on. So a very good numerical summary would consist of the frequency, which is the count. And so 19 respondents said their health status was excellent, another 12 very good, and so on. And the bottom of that column says lowercase n equals 50. That's the sample size. The sample size is always indicated by lowercase n, and in this case 50 people responded, and if you sum up those frequencies, they would total to 50 because each person answered or provided only one of those particular health states. It doesn't really help somebody if you say 19 people reported their health status as excellent. You have to know out of how many to really interpret that figure. And so what we often present for really both categorical and ordinal variables is a relative frequency, which takes the frequencies and divides by the sample size. So 19 divided by 50 would come out 0.38 as a proportion. lots of times people are more comfortable with percentages, and so we multiply that by 100 and get to 38%. So the relative frequencies are probably the best numerical summary for both categorical and ordinal variables, and they would sum to 100% if you put them in terms of percentages. If you left them as proportions, they'd sum to 1. Now, the two rightmost columns, I've shaded out a little bit in gray, and these show cumulative frequencies and cumulative relative frequencies. These are only appropriate for ordinal variables. They don't really make sense if you're summarizing a categorical variable. And the cumulative frequencies, you can think of these as running totals. So suppose you had a ruler and you put it underneath the excellent row. The cumulative frequency says 19 people reported their health status as excellent or better. If you slide your ruler down one row, 31 people reported their health status as very good or better. 40 people reported their health as good or better, anything above it. Once you get to the last row, which is poor, that health state, everyone has reported their health status as poor or better because that was the final response. And then the cumulative relative frequency just puts those into percentage terms, in each case dividing by 50. Okay? Now, graphical summaries, this is an example. This is an example of what's called a frequency bar chart. And in this case, I'm showing the distribution of responses to the question, which of these best describes your marital status? And the responses that we're giving people are married, separated, divorced, widowed, never married. And you might say there are other categories that could have been included, but suppose we gave these options. So there are 5 response options. There's no ordering here. One is not higher or lower, better or worse than any of the others. So this is a categorical variable, and when you generate a graphical display for a categorical variable, you want to use what's called a bar chart. And the distinction here between this and what I'm going to show you in a minute is there are spaces in between each bar. You don't want to run the bars together, because when you run them together, that gives the impression of a continuum, that one category runs into the next, and that's not the case here. And the y-axis, the vertical axis on the left-hand side, shows frequencies or counts. So it looks like about 25 people reported that they were married, maybe 5 were separated, 8 divorced, 2 widowed, and maybe 10 never married. The next chart is, this is called a relative frequency histogram. So let me start with the last word, histogram. So this is a graphical display of those responses we saw to the health status question. So a histogram is appropriate for an ordinal variable. Bar chart is for categorical. So if there's no ordering, that's a categorical variable. You want spaces in between. Whereas health status is an ordinal variable, poor is definitely less than fair, less than good, and so on. Now you can reorganize this and start with excellent on the left side down to poor. That doesn't matter, but you can't rearrange the categories in between because there is an ordering. And so because there's an ordering, we have no space in between to indicate that there's a continuum. At some point, a person judges their health status to be poor, or they move over to the next category. The y-axis, the left-hand axis, in this case shows what we call relative frequencies. So the previous graph had frequencies on the y-axis. You can also produce a relative frequency bar chart. It just depends on what you're showing on the y-axis. The pictures are identical in terms of scale. It's just that the scaling is different. So here I'm showing percentages on the y-axis. You can also produce what's called a frequency histogram and just show the counts on the y-axis. It's totally fine. You just want to be sure that you clearly label your y-axis. And again, whenever you put together a graphical display, the point is to convey to someone what you're seeing in the data. So this picture shows that lots of the participants in this sample reported their health status as very good and excellent, and fewer in the lower health status categories. A question someone raised is, can we say that an ordinal is a special type of a categorical variable? Well, both ordinal and categorical are variables where there's a fixed number of categories. The difference is whether there is ordering or not. So that's really the distinction between those two types. Okay, so now let's talk about continuous variables, which also come up a lot in public health and medical research. And these are, again, quantitative measurement variables, and a good example might be systolic blood pressure. And when we have a continuous variable, there are several ways we can go about summarizing that variable. A very standard summary consists of these three statistics. The sample size, suppose we have a sample and of 75 individuals, and we measure blood pressure for each of them. X bar is the symbol for the sample mean, and in this case, the sample mean blood pressure is 123.6, and S stands for the sample standard deviation. So these three statistics give the reader a sense of how many people were involved, the size of the study, what a typical value looks like, that's what the mean represents, and the standard deviation gets at how variable the blood pressures are. In particular, how much on average do blood pressures vary from the mean blood pressure. So the sample mean, people are usually very comfortable with the way that's calculated. You add up all the blood pressures and divide by 75. The standard deviation, the way you compute that, if you remember, if you've taken stats before, you take each person's blood pressure, subtract the mean, so you get an idea of how far they deviate from the mean value. And really what you want to do is get the mean of those deviations. The problem is, if you sum the deviations, you will always get 0. That's a property of the mean. The positive deviations will always equal the negative deviations, and they essentially cancel each other out. And so to get the standard deviation, we square the deviations and then do a square root at the end to get back to our original units. So the way we interpret the standard deviation, it tells us, gives us a feel for how close values are to the mean value. Now, just to give you a comparison, suppose we had a second sample in which we measured blood pressures, same size, 75 people. The mean is a little bit higher, 5 units higher, and the standard deviation is 6.4. So if you saw these two sets of statistics, you have two samples of equal size. The means are different by about 5 units, and in terms of blood pressure, that's not a huge difference, but the standard deviations being different in the second sample, a standard deviation of 6 as compared to 19 says, in that second sample, the blood pressures are much more tightly clustered together. They're much more tightly clustered around the 128. They don't deviate from that value too much. Okay? Now, there are other statistics that we can use to summarize a continuous variable, and you may have seen these before, and these are the medians. Sometimes we use the mean to summarize a typical value. Sometimes we use the median. And the distinction is, if you have a sample and you have no outliers or extreme values, then the typical summary would consist of the sample mean and the standard deviation. These will summarize, again, what we call a typical value, and in statistics we call that the location of the sample, and then how variable the data are. When there are outliers, though, and what I mean by that is values that are either extremely large or extremely small as compared to the rest, then the mean and standard deviation get affected by those. Suppose you had a sample of 6 blood pressures. Now, that's not a very big sample, so we don't need much in the way of analysis. But suppose we had 6 people, and the blood pressures were 120, 125, 130, 122, 128, and then we had somebody who was 160. Well, that person's value of 160 is quite a lot bigger than the rest. If we calculated the mean of those first 5 that I read, the mean might be around 125. But when you throw in that 160, it pulls the sample mean up, and it might give you a sample mean of, say, 135, when really nobody looks like 135. And so extreme values can affect the calculation of the mean, making it no longer representative of a typical value. So when there are outliers, people generally prefer the median value. The median is the middle value, and the way you calculate it is you order your data from smallest to largest, and then you choose the one number sitting in the middle. So if you have a sample of, say, 9 people, You order their blood pressures or whatever you're measuring, smallest to largest. The fifth value will be the median. There are exactly 4 below it and 4 above it. So it's considered the middle value. Another way to say it is half of the values are above and half of the values are below it. So if you decide to use the median to summarize a typical value, what goes along with that to round out the summary in terms of variability is what we call the interquartile range. So the interquartile range is defined as Q3 minus Q1. Q3 is the third quartile. That's the value that separates the top 25% of the data from the rest. And Q1 is the bottom quartile, or the first quartile. That separates the bottom 25% of the data from the rest. Sometimes people call the median Q2. If Q1 is the value that cuts off the bottom 25% and Q3 the top 25%, Q2 is the median, and that falls in between. So one way to determine whether there are outliers is to look at the first quartile minus 1.5 times the interquartile range. So you figure out the interquartile range, multiply that by 1.5, and that's a fixed number, and then do your first quartile minus that, and that will give you a lower cutoff. You do an upper cutoff of the third quartile plus that same amount, and then if you have any values below your lower cutoff or above your upper cutoff, that would indicate that they are outliers, in which case you should summarize what a typical value looks like in variability with the median and the interquartile range. Okay, some of you are asking a few questions, so let me try to answer some of those. What if there are repeated values? So if you have a pen, write these numbers down. I'll make up some numbers for you right now. And I'm just going to make this a small sample. Suppose you had a sample of, let's say, 5 people, and we're looking at blood pressures. Say their blood pressures are 120, 122, 122, 125, and 130. Okay? So I've ordered them smallest to largest. There are 2 values of 122. The median is the third smallest value, the second 122. So it doesn't matter if there are repeated values. You just count them as separate values and order them and choose the middle value. Just to take this one step further, keep those 5 numbers in a row and now add 160. So that would be a 6th number. If you have an even number of values, then your median is defined as the mean of the middle 2. So you take 122 plus 125, add those and divide by 2, your median would be 123.5. That's exactly in between those 2 numbers. A question also someone raised, how do you figure out the quartiles? Well, go back to, this is a very teeny tiny example, but when you figure out a median, you order the data and choose the middle value. To figure out the first quartile, just look at the lower half of the numbers. So 120, 122, and 122. The middle value of those is 122. Take the up, so that would be Q1. Take the 3 numbers at the top. I'm leaving off my 160 for a moment. The middle number of those top 3 numbers would be 125. That's Q3. I hope that's clear. And someone just asked, will these slides be available? Yes, they will be available on the website, and there's a link on the front of this. We can maybe make this available. I'll speak to Heather at the break and come back on the slides being available. Okay, so I'm going to keep going. All right, so sometimes you see tables like this in papers. So let me just point out a few key things in a paper like this. So first of all, this is a study, and it's looking at baseline characteristics of participants according to their soft drink consumption. This is a study I happen to be involved in, and we were relating the number of sodas that people drank to cardiovascular outcomes. And so people were categorized as having less than 1 per day, exactly 1 soft drink per day, or 2 or more. So first of all, our main exposure variable or risk factor was the number of soft drinks. People could report any number of soft drinks consumed, but we lumped them into these 3 categories because there were some people who had, were drinking lots and lots of soda, but we wanted to have reasonable numbers in the groups. So we put these 3 groups together for analysis. So this would be an example where we measured something that was continuous, but we created an ordinal variable for analysis. So the number of soft drinks is ordinal, less than 1, 1, greater than or equal to 2. Now, age in this example is a continuous variable, and what's being reported, now there would be in the paper a footnote, which I've chopped off, that would tell you what the statistics are that you're looking at, but you see the age is summarized in the top row, and what you're getting there are the mean and the standard deviation for the ages of participants in each of these groups. So the participants were in the ballpark of, 56, 53, 51 in each of the soft drink categories. And the variability in age, the standard deviations, were similar. Okay? Now, I want to just point out another thing right underneath that. Sorry, my red line is leaning on it, but then we see the percentage of the sample who are male. So that's a dichotomous variable that we're summarizing with a percentage. Systolic, diastolic blood pressure are both continuous variables, and you're seeing means and standard deviations. Just want to point out one more thing. Down near the bottom of the table, you have triglycerides. And once again, we have means and standard deviations. Now, in this example, the standard deviations are very, very large as compared to the mean values. And that's a flag. If you see standard deviations that are really large or even close to or exceeding the mean value, then that sometimes suggests that the data are very skewed. And triglycerides in practice happen to be a characteristic that where people, you have lots of people are in the range, like you see here, of 140, 150, but then some people have really extreme values, which are affecting the measures of the mean and the standard deviation. So this would be an example where we probably should have presented medians and interquartile ranges. They might have provided a better summary. Okay. There's one question someone raised. If you're looking for the first quartile, would you calculate the median or the mean of that half of the data? You would calculate the median, sorry. So you separate the data into lower half and upper half, and it's like you're doing a median of the bottom half, that's Q1, and a median of the top half, that's Q3. Okay? So a graphical display for a continuous variable is one like this, which is called a box and whisker plot. And you might think that's a weird-looking picture, but once you understand what it's showing, I think it can be useful. So a box and whisker plot is one where you show the range of the data, the minimum to the maximum, with a horizontal line. Now, you should have a scale running across the bottom, but I just want to point out the elements of the graph for you. The leftmost vertical line is the first quartile. Then there's the median, and then there's the third quartile, and you connect those with a box. Statisticians aren't very creative when it comes to labeling things, so they call this a box and whisker plot. So the horizontal line shows you the range of the data, how much spread there is from the smallest to the largest. The box in the middle contains the middle 50% of the data, because that's the definition of the Q1 to Q3. The median is where it separates the top half from the bottom half. So a really useful way to use these graphs is with what's called a comparison, side-by-side box and whisker plots. So here we have two samples. I've just labeled them 1 and 2, the red being 2. So, for example, in sample 1, in the black, roughly 75% of the participants have blood pressures below 130, because that's the value of the third quartile, the rightmost vertical line. That compares to half the sample in the red group, sample 2, having blood pressures less than or equal to 130. So when you're looking at these things side by side, you can see how the distributions compare. So the middle 50% of sample 2 is really shifted to the right, or is higher than that for sample 1. So the blood pressures in sample 2 are in general higher than those in sample 2. Okay? Let me give you a few questions to think about. What type of display is this one? Okay. So this would be an example of a relative frequency histogram. And so there's a couple of pieces here. relative frequency because the vertical axis shows percentages as opposed to frequency, which would just be counts. Histogram, because this is showing a disease stage, which is ordinal. There's definitely an ordering, and so we run the bars together. That's a histogram. How about this one? Suppose this is a picture of systolic blood pressures in men 20 to 29 years of age. What's the best summary of a typical value here? Okay. Good. A lot of you are sending me in your responses. So this would be the mean value. Now, your choices for the responses should be between the mean and the median, because the mean and the median summarize what a typical value looks like. You choose the mean when there are no extremes, no outliers, the median when there are extremes. A picture like this, yes, there is some spread in the data, but there's nothing really trailing off on the right end or the left end. So in this case, the mean would be the more appropriate summary. When data are skewed, the mean is higher than the median, true or false? Okay. Now, you all can't see the responses coming in, but there's some true and some false. It's actually false, and it depends. A lot of you now are saying depends. Good. So it depends. If the extreme values are on the high end, that would pull up the mean, making it potentially higher than the median. If the extreme values are extremely low as compared to the others, it could pull it in the other direction. So the correct answer here would be false because it depends. What about this picture? The best summary of variability for the following continuous measure would be what? Okay. Good. So a lot of you seem to be giving this response. Come on. Interquartile range, because here, this particular box and whisker plot would suggest that there are extreme values on the right side, as indicated by that long tail. So that means that because each of the sections of this box and whisker plot, and by sections I mean from the minimum to the first vertical line, the first to the second vertical, the middle to the rightmost vertical line, and then the leftmost to the end, each of those sections of the graph contains 25% of the data. If those are roughly equal in length, that would suggest the data are evenly distributed, but because it's much longer on the right, that means there are outliers on the right. So you'd want to use the interquartile range. Okay, so here's a summary slide that just tries to summarize what I've just said. So if you have a dichotomous or categorical variable, the best numerical summary would be frequencies, and really preferably relative frequencies, so you build in your sample size. If you want to summarize those variables graphically, bar charts, either frequency or relative frequency would be the best. If you have an ordinal variable, you can use that frequency distribution table with more detail, so frequencies, relative frequencies, and then the cumulative values if you're interested. And histograms are appropriate for summarizing. A continuous variable, you'd use the sample size, and either the sample mean and standard deviation, they go as a pair, or the median and the interquartile range. They would go as a pair if you have outliers. And outliers can be judged by that little rule that I gave you, or you can judge that from your own professional experience. You know, you get the feel for working with something, and you can judge whether something really is extreme as compared to the others. And if you were to present it, you would just justify that. And then the graphical display would be the box and whisker plot. All right, so I'm going to move on. I think I've got the questions answered, I hope, that you've raised so far. Again, we'll have time at the end, but I'm just going to shift gears a tiny bit and now talk a little bit about probability. And so there are lots of times that we have to deal with probability, and so let me just throw out a few examples to you, and then I'll try to get to some of the conceptual issues. So here's a little table showing blood pressure categories: optimal, normal, pre-hypertension, or hypertension in men and women. If we were to select someone at random, what's the probability we would select a male with optimal blood pressure? Okay. So a lot of you are sending this in. Great. So it would be 20 out of 150. Now, some of you said 20 out of 80. Now, the correct answer is 20 out of 150 because what I'm asking here is from among this pool of 150 men and women, and I realize I didn't say all that at the top, but it's implied, from among all of these people, what's the chance that I choose a person who is both male, sex, and optimal blood pressure? It would be 20 out of 150. If I had asked the question, what proportion of the men have optimal blood pressure, that would be 20 out of 80. Or if I asked the question, what proportion of those with optimal blood pressure are male, that would be 20 out of 25. So I'm going through that quickly, but those are different questions that would require different responses. So how about this one? What's the probability of selecting a patient with pre-hypertension or hypertension? Okay. So this is 95 out of 150. Good. A lot of you are getting this, and someone asked the question, how will we know in the exam if there's more information we should know? Those questions have been reviewed and vetted, and those questions, I hope, are very, very clear. So this is me trying to abbreviate and fit things on a slide. So I apologize for creating some confusion there. Okay, good. How about this one? What proportion of men have prevalent CVD? Okay, so many of you are answering 2 or 3. Now be careful. This one, there needs to be some totals around on the right-hand side and at the bottom. So the first column is the number with CVD. The second column is free of CVD. So the proportion who have prevalent CVD would be 35, and now we're just looking at the men out of a total of 300. So it's not 35 out of 265. That's actually something else. That's an odds as opposed to a proportion. We'll get to that in a minute. But you need your total to get this figure. What proportion of patients with CVD are men? Okay, good. A lot of you are getting this, which is great. So this would be 35 out of 80. So you want to look at the total number with CVD. That would be 80, the sum of the first column. And of that group, the number who are male is 35. Now, these last two examples are examples of what we call conditional probability. What we're doing is, rather than using the total in the bottom right corner of the table, like we were on those last couple of examples where it was 150 people, now we're subsetting the population. Sometimes, in the last example, we looked at just those with optimal blood pressure. Sorry, we looked at just those with prevalent CVD. I said it wrong. The last example, we looked at just the men, and now we're looking at just those with CVD. So we're subsetting the population by their sex or by their CVD status, and then doing our probability. These are examples of what we call conditional probability, where you condition on or focus on or subset based on a specific condition. And conditional probability comes up a lot when we do statistical analysis or when we're analyzing laboratory data or test results. So here's an example. Our family history and current CVD status independent. So here's a little table which cross-classifies people by their family history of CVD and whether they themselves have CVD. Okay, so we know whether they have a family history, yes or no, and then we know whether they themselves have CVD. Now, independence, what I'm asking there is, does your family history affect the likelihood or the probability that you yourself have CVD? Well, to answer this question, we have to do some calculations. So first, I'm going to calculate what's the probability that a person has CVD, him or herself, given that they have family history. That vertical line means given or conditioning on. So what's the probability that someone has current CVD given they have a family history? So that means we first look at, I sometimes do the denominator first, look at just those people with a family history. So that's the second row of the table, the 90 plus 15 for a total of 105. And among those, exactly 15 have CVD themselves, or 14%. Now do the same thing. What's the probability that someone has CVD given there's no family history? So now I'm calculating the probability that a person has CVD when they have no family history. I first sum the first row, it's 240, and 25 people out of those with no family history have it. So now the question is family history independent of current status? And the answer here would be no, your family history actually matters. If you don't have a family history, there's a 10% probability that you yourself have CVD. If you do, that's actually increased up to 14%. So this would be an example where family history and current CVD are not independent. How about this one? Are symptoms independent of disease? Okay, so here's an example. Now, some of you are not answering anymore. Maybe you don't know, or you are getting tired of pressing the keys. But anyway, our symptoms, thank you, now a few more coming in. Are symptoms independent? So what we have to do is check. So let's look at people who do have symptoms. So that's the first row of the table. What's the probability they have disease? Well, that would be 25 out of 250, or 10%. Now look at people with no symptoms. 50 of them out of 500 have disease. That's also 10%. So regardless of your symptom status, it's still a 10% probability you have disease. So this would suggest that symptoms and disease are independent. So if the probabilities are the same, then the two things are said to be independent, okay, or unrelated. Some of you asked questions about the slides. Are the slides available? And Heather, looks like I'm seeing her saying that the slides have just been posted. So you should be able to see the slides. And we'll take a break in a little bit, and we can be sure everybody has those or can get access to them. Okay? All right. So all those probabilities that we just did require you to have a cross-tabulation, a table, so that you can actually figure out how many people meet the condition I'm asking and what's the denominator, whether it be that number in the bottom right or maybe the sum of a row or a column, depending on what you're looking at. There are also probability models or mathematical formulas that can be used to calculate probabilities. And there are a couple of popular ones. Now, I'm just going to give you some of the details. I'm not going to go into a lot of depth on these things, but just try to give you a flavor of a couple of popular probability distributions. And I suspect you've seen these if you've had this course before. So a popular probability model for a dichotomous variable, one with two possible outcomes, would be the binomial distribution. And so the idea here is each person can experience one of two possible outcomes. And when we look at lots of people taken together, the likelihood that one person is a success, and we usually call the response options success and failure. They can be the yes, no responses. But the likelihood that one person has a positive or a successful response is independent, has nothing to do with the likelihood that someone else has that. And the likelihood of success is the same for each person. And if you meet these criteria, then you can use this equation, which is a binomial distribution model, to calculate probabilities. And in this case, the mean number of successes that you might experience in a sample is your sample size times the probability of success the variance is the sample size times the probability times 1 minus the probability. So just a little example. Let's suppose that we're talking about a situation where we're looking at people going in for a particular surgical procedure, and we're worried about risk of complications. And so people either suffer complications or they don't. And let's say there's a 10% chance that someone has complications. Let's say we're including some minor complications, because that would be actually a bad number. But let's say 10% that, something happens, and they're not all horrible things. And does this meet the criteria to be a binomial distribution? Well, people either have complications or don't. If we look at several people, presumably the likelihood that one person has complications should have nothing to do with the likelihood that someone else has them. And assuming that all the patients have a similar background, meaning they're not at high risk or don't have other comorbid conditions, then the likelihood of developing complications should be the same for all people. If you took a sample of 50 people, how many would you expect, or what would be the average number to have complications? It would be 50 times 0.1 or 5. Okay? Another probability model that comes up is the Poisson distribution. It's for a similar application, but a slightly different twist on it, where, again, you meet the same criteria. It's a yes-no type of outcome. The replications are independent. But this is used often to model rare events, so things that occur very rarely, which we do face in public health. There are lots of times we're looking for things that thankfully don't affect lots and lots of people, and we might use the Poisson model. And here's the mathematical equation. And you won't have to memorize all of these things. Some of you are asking these things. Just want you to understand the big picture. Binomial, 2 possible outcomes. Poisson is also 2 possible outcomes, but something for more rare events. Okay? I'm just giving you the detail. I suspect some of you may have seen it, but don't worry about some of these minute details. I know you're preparing for the exam. It's really big picture. Okay? I apologize. You hear the sirens going by. My office is on a medical campus, and so this is what I hear all the time, and I could probably tune it out a lot better than you can, but sorry about that. Okay, so let's talk about the normal distribution model. This one comes up a lot in practice, and this is a model for a continuous outcome. And there are some very specific features about the normal distribution. One is that the mean is equal to the median is equal to the mode. And so this is an example. The normal distribution is one where if you draw a graph, you often follow what we call a bell-shaped curve or a normal distribution curve. And so the mean is sitting exactly in the middle. In fact, for the normal distribution, the mean value is equal to the median. Now, just a few minutes ago, we said that's not always the case. If you have outliers, extreme values above and below, or high or low, the mean and the median will not be the same. But if you are in the situation where they are, your data might follow what's called a normal distribution. It's also true that the mean is equal to the median is equal to the mode. The mode is what's called the most frequent value. So the highest peak on this graph would be what we call the mode, the value that occurs most frequently. And for a normal distribution, not for all distributions, but for the normal, the mean is equal to the mode, equal to the median. Now, if you know or are told that something follows a normal distribution, again, how would you know? Well, you could graph it out and eyeball it and see if there's a peak in the middle. And really what it means for something to follow a normal distribution is that most of the people would fall in the middle of the distribution. As you get to extremely high values and extremely low values, you have fewer and fewer people. And that actually is what happens for many characteristics that we deal with. Blood pressure, for example, is a characteristic that lots of people are sort of in the middle, but there are fewer and fewer people with extremely high or extremely low blood pressures. It's the same thing is true if you're looking at something like body mass index. Lots of people are in the middle, but as you get extremely high and extremely low, there are fewer and fewer people. Now, there's one caveat there, and we use this a lot in public health just to track, especially children. we monitor their body mass index. We also monitor other things like their height and their weight to see if they're growing, and I'm going to put in quotes, normally. And what this means is, do children look like other kids of the same age and sex? So once you stratify by age and sex, then you can look at distributions. There are a few questions coming up. I'm not ignoring you, but some of these I have to put off to we have a break because I need to confer with some of my colleagues to make sure I'm answering them correctly, okay? So let me give you a little example. So body mass index. So body mass index, I suspect you've heard of it before. What it is it's your weight in kilograms divided by your height in meters squared. So it's kind of a weird units that are used for body mass index, but think of it as an adjusted weight. You know, if you're looking at weights of people, someone who's 6'5" would hopefully weigh a different amount than someone who's 5'5". So BMI is one way that we take height into account, and there are other ways, but this has become a popular metric that's used. So for men age 60, it's normally distributed with a mean of 29 and a standard deviation of 6. So once we know, or are in this case told, that something follows a normal distribution, we can go ahead and draw the bell-shaped curve. We can also plug in the mean value right into the middle, and we can plug in, now what I've done here is I've counted 3 units above the mean and 3 units below the mean. And what I'm counting by are units of the standard deviation. For the normal distribution, if you start with the mean right in the middle, there's where I put my 29. If you count 3 standard deviations above the mean, that should put you pretty much at the end of the curve. If you count 3 standard deviations below the mean, that should put you pretty much at the end of the curve on the low end. Now, does it mean that there's nobody with a BMI above 47 or below 11? No, it just means that's very unlikely, okay? Now, one thing I skipped over, can I just go back here? So for the normal distribution, that first property, I said that the normal distribution is symmetric about the mean. What that means is the right side of the curve looks just like the left side of the curve. So they are mirror images of one another. So the probability that someone exceeds the mean value is the same as the probability that they fall below it, and it's equal to 0.5. Now, one other twist here. All of a sudden now, I'm calling the mean mu with the Greek letter mu. It looks like a script U. When you're talking about probability, you're talking about population. When you're talking about samples, we're using the sample mean. And so I'm talking more theoretically right now, and so I'm using that indicator for the mean as the population mean value. The second bullet here says that the mean and the variance, mu and sigma squared. Now, when you're dealing with a sample, the mean and the variance would be x bar and s squared. The mean and standard deviation for a sample, x bar and s. But here we're talking population setup, so I'm using the Greek letters. These completely characterize the distribution. If you know the mean and the population variance, you know everything about that distribution. I already told you that the mean is equal to the median is equal to the mode. Now, it turns out for a normal distribution, about 68% of the values fall between the mean plus or minus 1 standard deviation. This is true for all normal distributions. About 95% of the values fall between the mean plus or minus 2 standard deviations, and almost everybody is between the mean plus or minus 3 standard deviations. So sometimes, say you go to the doctor and you have a lab test done. You get a regular physical, they take your blood, and they do all kinds of things, your cholesterol level and all kinds of stuff, and they mail it back to you a week later, and it gives you your value, and then sometimes there's a little indication next to your value, and it might say within normal limits. What that means is your value was within the mean plus or minus 2 standard deviations for that particular characteristic. And where do they get that? Well, they look at all patients who have had that particular test. Or they might stratify it by sex or even age. But oftentimes when you have lab values measured and reported back to you, they'll indicate whether your values look normal, and they're often looking at the mean plus or minus 2 standard deviations. Now, why do they look at that? Because that's really where 95% of the people lie. it's not a problem if you're outside of the mean plus or minus 2 standard deviation. It just means that you're in the extreme 5%, and it might be worth them looking more deeply into it. That's all. Okay, so back to our example. I'm sorry, I had skipped over that. I was getting sidetracked by some of the questions coming up. So here we have BMI for men age 60 is normal, so we can draw a picture, put in our mean, and our 3 multiples of the standard deviation. Suppose we ask the question, what's the probability that a male has a BMI less than 29? So if you look at this figure and you look at where 29 is, well, 29 happens to be right in the distribution, and we're looking at the area under the curve below that value, so that would be 0.5 because it's exactly half the curve. Okay? What's the probability that someone has a BMI less than 30? Well, now, because I'm not asking a question about any one of those multiples, those numbers that you see on the bottom, I've got to do something different. And so to calculate probabilities of the normal distribution, we use what's called the standard normal distribution. Somebody just wrote it's greater than 0.5. That's absolutely true, and we can actually figure out what it is exactly. So the standard normal distribution is Z, and what Z stands for is a normal distribution, so still our bell-shaped curve, but a mean of 0 and a standard deviation of 1. So that's what I've drawn here. I put 0 in where the mean value goes, right in the middle, and then I'm counting out by units of 1, the standard deviation 3 units above and 3 units below. And we use this standard normal distribution to answer our question about the BMI data, which is also normally distributed, but with a different mean and standard deviation. So what we do is we standardize. So we take our value of 30, the BMI of 30, and we standardize it. In other words, convert it onto the Z-scale. So we subtract the mean of 29 and divide by the standard deviation of 6, and it comes out to be 0.17. What that means is a BMI of 30 on that distribution is 0.17 standard deviations above the mean. Now think of where 30 was in that picture of BMI. It was just to the right of 29, which was the mean. 0.17 is just to the right of 0, and it's by the exact same amount. So I'm sure you've seen, lots of textbooks that have tables of probabilities for the standard normal distribution, or you can get these figures out of a statistical computing package. But you should get the feel for, does this look like a reasonable number? If you calculated a Z-score of 0.17, definitely someone wrote a response that when I first posed the question, the probability is above 0.5, but it's not 0.9, but it's something just above 0.5, okay? So another application that people often use, suppose we wanted to compare blood pressures. Suppose for men age 50, blood pressure is approximately normally distributed with a mean of 108 and a standard deviation of 14. Suppose for women of the same age, blood pressure is approximately normally distributed with a mean of 100 and a standard deviation of 8. If a male has a blood pressure of 140 and a female has a blood pressure of 120, who has the higher blood pressure? What I'm asking is a 140 for a man worse than a 120 for a woman? And how would you know? Okay, well, the issue here is that you're comparing apples and oranges. So what you need to do is compare things on the same scale. So what does that 140 look like in terms of a Z-score? So if we take the 140 and subtract the mean for men and divide by the standard deviation, we get 2.29. What it means is that value of 140 among men is 2.29 standard deviations above the mean. If you do the same for the woman, she's actually 2.5 standard deviations above the mean. So that would be more extreme, further into the tails of the distribution. So in this case, the woman's value, even though absolutely 120 is less than 140, in relative terms, that would be the more extreme value. And you have to use Z-scores So you're comparing apples and apples. Okay? Percentiles. We often look at percentiles with the normal distribution, and a percentile is defined as the score that has a certain percent of scores below it. For example, a 90th percentile is a score that has 90% of the scores below it. Q1 is actually a percentile, 25th. The median is the 50th, and the third quartile is the 75th. There's a little formula for calculating percentiles, and it's basically taking that z-score formula and turning it around. And so if you want to calculate a percentile, you take the mean, you add the z-score for a particular percentile, and you can figure these out from the z-table and multiply it by the standard deviation. So for example, the z-score for a 95th percentile is 1.645. So if you wanted the 95th percentile of BMI in men for that example we were working on, it would be the mean, 29, plus 1.645 times the standard deviation of 38. And what it means is 95% of the BMIs in males age 60 are 38.9 or lower. Okay? Now, central limit theorem. So the central limit theorem, I'm just going to mention this because it's very theoretical, and it underlies really all of what we do in applied biostatistics. But the gist of it is, if you have a population and it's got some mean and some standard deviation. Now I'm using the population figures, mu and sigma, as opposed to x bar and s, because we're talking population. If we take samples of size n, which is what we do in practice, we take a sample of 100 people or 50 people or whatever, as long as the sample size is large, and usually 30 or greater is considered large, it turns out that the distribution of the sample mean, that is, if we take samples over and over, and each time calculate a sample mean, and then we graph it out, that distribution is approximately normal. And therefore, we can use the normal distribution to calculate probabilities, which is what we do in practice. Now, this Z formula isn't exactly the same as that Z formula I used a minute ago. In the denominator, it has something sigma divided by square root of n. That's what's called the standard error. You may have seen the standard error when you look at papers where people are summarizing things. The standard deviation describes variability in observations. So as we started, for a particular characteristic like blood pressure, we might calculate the mean and the standard deviation if we wanted to describe how variable blood pressures were in a sample. The standard error, on the other hand, gets that variability in the sample mean. And you might say, well, why would you ever want to get variability in a sample mean? Well, in practice, we summarize something with a mean value, and then what we want to say is, this was only one sample. Someone else might take a different sample and get a slightly different mean. How variable are the means? And that's where you would report the standard error to describe variability in your sample means. And this standard error term is going to come up when we get to some of our applications. Now, what I'd like to do, if it's okay with you, is take a 5-minute break here. I know we have a ways to go, but a number of you have asked about slides. And so I want to be sure you have a chance to get slides. So I'm going to ask Heather, who I hope is still with us, to see if you can get access to the slides, because some of you are wanting to write things on the slides. So let's take a 5-minute break, okay? And then I'll come back and pick it up in just about 5 minutes, and I'm hoping that you can get slides. Okay, the link has been posted. I'm hoping you can use that link to get the slides, and we'll give you a moment to do it. One of the attendees has just posted it again, I see, in And so hopefully people are seeing. Can some of you respond to me if you're able to get the slides? I just want to be sure before I pick it back up. Okay, great. Thanks a lot. Okay, good. All right. So it sounds like you all have the slides. Let me just give another minute in case people took me up on the break offer and ran out for a moment. And we'll also do a little bit longer break shortly so that you can get a drink and things like that. Okay, so a couple questions that have come up. You will not need a calculator on the exam, so I'm showing you the calculations just because I want you to understand what things are. But the point is for you to understand this material and be able to apply it at a higher level. Some of you also asked if this webinar will be available after the fact with audio, and the answer is yes, you'll be able to get the audio available after. So if you're interested in listening to this again, it would be hard for me to understand why you'd want to do that again. But you may want to, and you can. A couple of questions that you're all asking. Do you need to memorize formulas? No, you don't need to memorize formulas. Again, it's more big picture. Okay, so the questions are really bigger picture. You don't need the formulas. What's the difference, for example, between the binomial distribution formula and the normal? And the difference is binomial is for a dichotomous outcome, whereas normal is for continuous. All right, so let me try as we go through. I don't want you to feel, I'm having, I have to balance how I explain this to you, so I'm trying to go through it in detail, but I'll try to keep pointing out the big picture concepts of it, okay? So you don't need to memorize formulas. All right. So let me keep going. All right. Okay. So there are two areas of statistical inference, and so remember at the very beginning, the first slide I said was there's descriptive statistics and statistical inference. Descriptive statistics, just like it sounds, is you describe the sample. What's important there is how do you describe the sample? You have to be able to distinguish the variables, and you have to appropriately summarize, for example, continuous variables. Should you use the mean or the median? And when would you use each? Those would be the bigger picture type of questions. You'd also, when would you use a bar chart versus a histogram, that kind of thing. If you had a normal distribution, even though I showed you detailed calculations, if a question, say, was posed on the exam for that BMI example, and we asked what's the probability someone's BMI was less than 30, a lot of the questions are multiple choice. If you had an answer like 0.55 versus 0.95, you'd be able to distinguish those two thinking about the whole distribution, okay? So now we're into statistical inference. And there are two areas of statistical inference, what we call estimation and hypothesis testing. There's actually a relationship between the two. I'll explain them to you separately, but then I'll show you how they link together. So in estimation, the idea is we don't know anything about the population parameter. So what we do is we take a sample, we use our sample data to estimate that unknown quantity. In hypothesis testing, we actually start at a slightly different place. We start by putting up a hypothesis, making a statement about a parameter, and then using data to see whether they support that particular statement or not. Okay? Again, when you try to get to what analysis do I do when, it comes back to, well, first you have to figure out what kind of an outcome, or what's the variable that I'm dealing with. Is it continuous, dichotomous, categorical, or time to event? Now, I'm throwing in that last one, time to event. It's kind of a mixture of the ones that we've already talked about, so I'll bring that up a little bit later on. So again, whenever you look at analysis, think about what kind of variable am I analyzing. The next thing that you have to think about is, how many groups do I have? Do I just have one group? Do I have two independent? And what I mean by independent here is two physically separate groups, or do I have two matched or paired groups? I will explain that to you in just a minute. Or are there more than two groups? Remember that example way back, seems like a long time ago now, with the soda? We had people who were drinking less than one, greater than or equal to two. So that would be more than two comparison groups. And then we have to look at what's the question? Are we trying to look at association between lots of variables? That would fall into what we call regression analysis, and I'll get that to you. Now, someone's saying they still can't find the slides. There is a link. The link is on the national board, www.nbphe.org/webinars. That's where you'll find it. Okay. All right. Okay, so estimation, as I said, it's determining likely values. That's an important word, likely values for unknown population parameters. And there are two kinds of estimates. One's called a point estimate, which is the best single number estimate for a parameter. So that's your best estimate based on the data of what you think a value is. And then there's a confidence interval estimate. And a confidence interval is a range of values for a particular parameter. And the confidence interval starts with our best estimate, and then we add and subtract what we call our margin of error. And that margin of error really consists of two things. I put T in there, and T stands for a value from a probability distribution to reflect a level of confidence that we choose. And we multiply that by the standard error. And that's that estimate of the variability in our mean value or whatever it is that we're analyzing. All right, some of you are asking me to stop for a minute. You're trying to get the slides. The slides are under Biostatistics on the first page in blue font. It'll say PowerPoint slides. Okay, so that's how we go about, let me just back up to this. When we do estimation, we generate confidence intervals. Now, if we, when we're in an election year, and at that time, we have pollsters who are taking polls all the time and looking at, the likelihood that certain groups of people in a certain area or, of a certain background are going to vote for a particular candidate. They'll often report, we did a poll and 40% of the people we surveyed indicated that they're going to vote for this particular candidate. And then often in small print, it'll say plus or minus 4% or plus or minus 3%. And so what that means is their best estimate is the 40%. But their estimate, what they really think is it's not exactly 40%. It could be plus or minus 4%, anywhere from 36 to 44%. That plus or minus value is the margin of error. Okay, when we do hypothesis testing, it's a slightly different approach. So here I'm writing out, I don't mean that it's this rigid, but these are the steps that are involved. So we set up our null in our research hypothesis. The null hypothesis is the no difference, no effect, no change situation. The research hypothesis is actually what we think to be true. And we select our what we call level of significance. I'll explain that to you in a minute. We choose a test statistic. That's a summary number of our data. We set up a rule to decide when to believe the null in the research hypothesis. We look at our data, and then we come up with a conclusion. And when we do hypothesis testing, we produce what's called a p-value. Yes, someone asked, research hypothesis is the same as alternative hypothesis. So you may have used that language before. But it's what you think to be true. Now, p-values, which is what we see often people are presenting, represent what we call the exact significance of the data. And the p-values are what we estimate to summarize just how significant our data are. And these get reported in the literature. These can be approximated with probability tables, or you can get them exactly with statistical computing packages. You'll be in the position in practice of interpreting p-values. If a p-value is less than or equal to alpha, now alpha is your level of significance that you choose. Most of the time it's 5%. Then you reject the null hypothesis in favor of your alternative. The p-value represents the likelihood of observing your data if the null hypothesis is true. So if the p-value is really small, what that means is it is very unlikely to observe the data you observed given the null hypothesis is true. So if the p-value comes out to be small, we tend to say we don't believe the null hypothesis to be true, we believe the alternative. And because the alternative or research hypothesis is what you think to be true, you want to see small p-values because they support what you think to be the case. Now, before we get into specific examples, there are some mistakes that we can make in statistics. And when we do hypothesis tests, there are really two kinds of errors that we can make. So first of all, let me tell you what I'm trying to get across with this little table. So the rows of the table indicate that the null hypothesis, that's H sub 0, the null hypothesis is either true or false. Now, by the way, there's a null hypothesis and an alternative. Sometimes we write that as H1. That's our research hypothesis. So in reality, either the null hypothesis is true or false. Because we're not willing to look at the entire population, instead we have a sample of individuals and we're looking at their data, we can't know for sure if the null hypothesis is true or false. So what we do is we run a statistical test. That puts us in one of the columns of this table. We run a statistical test, and the test tells us to either not reject the null hypothesis, in other words, believe it to be true, or to reject it and believe the alternative. Let's start with the rightmost column. If you reject the null hypothesis, and in fact the null hypothesis is false, you're in the bottom right corner of this table. And that means that's a correct decision. Your test told you to reject HO, and in fact it's really false, so that's the right answer. If you reject HO, and in fact the null hypothesis is true, you've made a mistake. Now you might say, well, how could that happen? Well, it could be in reality that whatever your intervention is, it doesn't do anything. But just bad luck, you got a sample of people who are not representative of the entire population. And your sample led you to believe that your intervention had an effect. That's a type 1 error. And that can happen. Now, when we do a statistical test, we set up our level of significance. That's the probability of a type 1 error. Usually we set that probability to be 5%. So when we run a test and we reject the null hypothesis, there's a 5% chance we made a type 1 error and a 95% chance we made the correct decision. So generally speaking, if we run a test and reject HO, we feel pretty comfortable that we've made the right decision because the probability all works in our favor that way. On the other hand, if we run a test and the test says do not reject the null hypothesis, then again, either that's correct because the null hypothesis is true, or we've made a mistake, and we call that a type 2 error. Unfortunately, we will never know in any situation which of these boxes we're in. All we know is that our statistical test tells us to either reject HO or don't. If you reject HO, you've either made a right decision or it's a type 1 error. If you don't, reject HO, again, it's either correct or it's a type 2 error. The difficulty when you don't reject HO is it's not as easy as it is with the rejection in that you can't fix the probability of a type 2 error. It's more complicated than that. So if you've ever read a paper and the author said, we didn't reject the null hypothesis, meaning they set up a study, they wanted to show that something had an impact, they weren't able to show it, and so what they'll often say is our study was underpowered. What that means is they didn't reject the null, and it's possible that they didn't have a large enough sample to show it. They're not coming around and saying, I guess we were wrong in setting this up. What they're saying is we might not have had a large enough study. Is there an easier way to memorize type 1 or type 2? Unfortunately, it sort of takes writing out a table like this and thinking about it this way. If you reject HO, you've either made the right decision or a type 1 error, and again, the probability of a type 1 error is your level of significance, which you fix to be small. Okay. So let me walk through some different applications for you. If you have a continuous outcome and you have one sample, then one of the analyses that you can do is estimating the mean value for that continuous outcome in the population. Now, an example of a continuous outcome could be blood pressure or cholesterol or BMI. I happen to live in the city of Boston, so we might want to estimate what's the average BMI in residents of the city of Boston. So that would be a continuous outcome, and I might take a sample of residents of the city of Boston and look at their BMI. So these are the formulas on this slide for confidence intervals. Now, many of you may have only seen the one in the bottom left, where you start with the mean value. So your best estimate of the mean BMI for all residents in the city of Boston would be whatever you observe in your sample, your X bar value. Then you add and subtract your margin of error. The margin of error is some number to reflect the confidence level you choose, and many times we use a 95% confidence level, and then that gets multiplied by the standard error, which is the variability in our point estimate. I've written two formulas here. The difference is only in whether you use Z, which is our standard normal, or T. Most statistical computing packages just show T throughout, and then they make adjustments for whether you have a large sample or a small sample. Let me just show you a little example. Suppose we want to generate a 95% confidence interval for the mean waiting time in the emergency department at a particular hospital. We survey 100 people, and we record what time they walk in and what time they're seen by a provider, and let's say on average they wait about 38 minutes. We calculate our standard deviation to be 9.5 minutes, so we can put together a confidence interval estimate. Now, I chose a 95% confidence level. What that means is I will be, at the end of this, 95% sure that the true mean falls in the range that I produce. You can choose other confidence levels. You could choose 90%, you could choose 99%. Now you might say, why don't you always choose 99%? And the response there is the higher the confidence level, the wider the interval. And so to be more confident, the interval is going to get wider. And so I can say to you, I can probably say this, I'm 100% sure, even though in statistics we can't ever be 100%. But I think I can say this. I'm 100% sure that the average BMI for residents in the city of Boston is anywhere from 5 to 500. It's a ridiculous estimate, but to be 100% sure you have to produce a wide interval. So that's the trade-off, and people have settled on 95% as a value that gives you some confidence. 95% is a high number, but not so high that the interval becomes too wide. Okay, so let me follow this through. So the confidence interval formula is here. So here's my mean value is 37. The 1.96 is the Z value or the T value for a large sample for 95% confidence. And 9.5 is the standard deviation that I was given or the variability in the waiting times over my square root of the sample size. If I carry this through, I get 37.85 plus or minus 1.86. 1.86 is my margin of error. Now, some people leave the confidence interval that way, the second to last line, and they'll say, my best estimate for how long people wait in the emergency department is about 38 minutes, plus or minus 2 minutes. Another thing that people do is they add and subtract that value, and they say something like, I'm 95% confident people wait anywhere from 36 to 40 minutes. Okay? A couple of questions have come up. The type 1 and type 2, just to go back for a minute, yeah, some people do describe type 1 as a false positive result and type 2 as a false negative. That is correct terminology for those. In terms of distinguishing between these formulas that I've shown here, some people would use the Z formula where only when the population standard deviation is known. In practice, we often don't know that, and so I'm just using the Z formula for larger samples, but that's theoretically correct, the person who's asking that. S here is standing for the sample standard deviation, and the someone asked to go over the sample mean and the standard deviation again. The sample mean, if you have a set of observations, so in this case, there are 100 people in the sample. For each person, we've measured how long they're waiting in the emergency department. My sample mean is computed by summing those 100 times and dividing by 100. The standard deviation, I calculate, if I were to do it by hand, which, by the way, I wouldn't, and I hope you wouldn't either, you'd take each of those 100 values, subtract the mean value, 37.85, square them, divide by n minus 1, and then take the square root. Now, a question from a few minutes ago was, why the n minus 1? When you calculate the standard deviation of a sample, you divide by n minus 1, even though I've been kind of loose in my description saying the standard deviation represents, on average, how far each person is from the mean value. That's a little bit loose because the denominator for that is n minus 1. Now, why do we divide by n minus 1? There are some technical reasons. Let me try to give it to you a little bit in plain English. When we get to doing statistical inference, we want to estimate the population variability based on our sample. If we were to divide by the sample size rather than the sample size minus 1, we would consistently underestimate the variability. So when you're calculating a standard deviation based on sample data, which almost always is what we have, if you have population data, you don't need statistics. So when you're doing any calculations on a sample, you always will be dividing by n minus 1. I hope that's clear. Okay, so now suppose that we want to go to a different situation. That example that I just showed you was a confidence interval estimate when you have a continuous outcome. So now I want to focus on what if you have a different kind of outcome, a dichotomous one. Let's say, for example, we're looking at a surgical procedure. It was a success or it was a failure. Someone goes into cancer remission, yes or no. This is a dichotomous variable and one study sample. Just to continue my example of in Boston, I could say, suppose we wanted to estimate the percent of people living in the city of Boston who meet the criteria to be obese. That's a BMI of greater than or equal to 30. So the idea is you have one study sample. On each person, you measure your outcome, which is a yes-no, and then you'll have your sample size. So the summary that you'll have is the number of people in your sample and then the number who meet your criteria, your particular question, and so you can calculate a sample proportion. That's the P with a little hat over it. Anytime you see a letter with a little hat, sometimes it's a squiggle, that means estimate. So for a dichotomous outcome in one sample, here's the formula for a confidence interval. Once again, you start with your best estimate, so that will be the sample proportion, and then you add and subtract all that stuff to the right of the plus minus is called the margin of error. There's the Z number that we would include for the confidence level, say 1.96 for 95%, and then all that under the square root is the standard error. Now, there's a condition for using this formula, and it's written just below it. It says the minimum of n times p hat and n times 1 minus p hat must be at least 5. What that means is, now remember, n is the sample size, p hat is the proportion of successes or the proportion of yeses. So the sample size times the proportion of yeses just gives you the number of yeses. So what that condition is actually saying is you need at least 5 people who are yes responses and at least 5 people who are no responses in your sample to use this formula. Now, for most of the things we deal with, we meet that criterion very easily. There could be a situation, though, where you might have 100 people and you're dealing with something that's so rare that only 1 or 2 would have the condition. If that's the case, then you wouldn't use this formula to generate a confidence interval. You'd use something called an exact formula. And that has to be done with a computer. It's done with some numerical simulation, and so it doesn't have a closed form formula like this. So just here, capture that last phrase, the exact procedures. Exact procedures are used when you have a dichotomous outcome and you're dealing with a very rare event, and you can't use these formulas involving the z-scores. So let me give you a little example. So I happen to do a fair amount of work on the Framingham heart study, and suppose we look at the Framingham offspring, who are the children of the original cohort participants, and we might have 3,500 odd of them. And in this case, we're looking at how many are on antihypertensive medications. So this is a yes-no response, and it turns out that 1,219 are. And we want to generate a 95% confidence interval for the proportion of people on antihypertensive medication. So here we clearly meet the criteria for use of the formula. We definitely have 1,200 on meds. That leaves about 2,300 not on meds. So we more than meet the conditions. So we can use the formula. Now, that 0.345, I got that by dividing 1,219 divided by 3,532. Okay, so that's my sample proportion. And I'm adding and subtracting. For 95%, the z-score is 1.96. And then under the square root, the proportion, 1 minus that over the sample size. So I take this one step further. My best estimate of the proportion of people on antihypertensives is 0.345, where the percent is 34.5%. The margin of error is 1.6%. If I go to that very last step, I could say I'm 95% confident anywhere between 33% and 36% would be on antihypertensive medication. Question someone asked is, can you repeat when exact procedures? You'd use exact procedures when you are dealing with a dichotomous outcome, but you don't meet this minimum criteria for use of this formula, so you don't have at least 5 successes and failures in your sample. Another question asked, would the exam ask you to interpret confidence intervals? Yes, very much so. So you'd be expected to do the kind of interpretations along the lines of these phrases that I'm giving you. And again, the test format is, many of them are multiple choice, so you might have some different statements, and then you would choose the one that's the most appropriate. So I'll show you I'll give you a common mistake that people might make. So in this example, the data here would suggest that anywhere from 33% to 36% might be on antihypertensive medication. Now, we're not saying that 95% of our sample is doing anything. We're saying that our best estimate for the proportion, okay, is what we're estimating here. Give an example when you would use an exact procedure. You'd use an exact procedure. Let's say we had a sample not of 3,500 people, but let's say we only had 35 people in our sample, and only 3 of them were on meds. Well, we don't meet that condition that you have to have at least 5 in each category. So in that case, if you only had 3 in the positive response, then you'd have to use the exact. Okay, so here's an example of a test of hypothesis, again, when you have just one sample. And sometimes these tests are called comparing against a historical or an external control. So you could have a situation where, let's say, in the city of Boston last year, a study was done and found that the mean BMI of residents of the city of Boston was 28. I'm making this up. We might hypothesize that this year our mean BMI is actually less than that. Now, why might it be less? Well, it so happens that we have a mayor who decided that he wants the city of Boston to lose 1 million pounds. And maybe people took him up on this challenge and have actually tried to do something about their BMI such that a year later the BMI on average would be less than 28. This would be an example where we do a one-sample test. We'd sample people this year, look at their BMIs, and compare them against that. If the average in this year's sample, how that compares to the value of 28. And we could do the same with the proportions. We could compare what we're seeing this year against, let's say, 60% of the sample last year met the criteria for obesity. Is it less this year? Okay, and these are the formulas. Again, you don't have to worry about the formulas. I'm showing you these because I suspect that this is how you went about doing these analyses before. Big picture. This is the setup when you have one sample and you're comparing against a historical or external control. The left side of this sheet is for a continuous outcome, the right side for a dichotomous outcome. And I'll show you some one more example. You could have a categorical or an ordinal outcome, and you do the same thing. Now, when you have categorical or ordinal outcomes, and you're comparing against some known values, you use what's called a chi-square goodness of fit test. It's not a z-test. You see on this slide, you could use a z-statistic or a t-statistic on the left side, a z-statistic on the right side. These are assuming that our samples are large enough to use the normal distribution. And again, that point about the exact procedures comes into play when you have a dichotomous outcome and you don't have enough individuals in each of your categories. Okay? Now, the goodness of fit. So this applies when you have a categorical or an ordinal outcome. And here, you don't have to make the distinction between the two. So let me give you an example. Lots of times we measure BMI. BMI is actually a continuous variable. People can have a value, anywhere from usually less than 18 is considered underweight, and people don't tend to go too much lower than that. Unfortunately, they can go very high. People can have, BMIs into the 40s and 50s when they're morbidly obese. But there are some clinical cutoffs that people use, and they classify people often as normal weight, which may not be a good term, but they do use that word, normal weight, overweight, or obese. So that would be an example of an ordinal variable. And let's suppose, just continuing our City of Boston example, that last year that 20% of our sample were normal weight, 40% were overweight, and 40% were obese. So let's suppose that's what the situation was last year. And now, given our mayor's initiative for people to drop some weight, to be more healthy, we're actually going to ask the question, is the distribution the same? So we would take a sample this year, look at people's weights, see how they fell into those categories, and then we would compare what we observed to these fixed values, 20%, 40%, 40%, and that would be done with a chi-square test. Okay? Now, it's often a difficulty, a challenge to get the right comparison. So all those examples that I just gave you compare against fixed numbers, what we had last year. And now some of you live in different cities than where I live. You could take information that you have in your city and compare it against what Boston reported. Is that the appropriate comparison? What's better often, or viewed as a better way to go at questions like that, is to actually have two comparison samples. And so, again, we'll start with the case where you have a continuous outcome, maybe something like blood pressure or weight or cholesterol, and you want to, say, put forward an intervention to lower blood pressure, lower weight, or lower total cholesterol, and rather than relying on an external or a historical control, you actually have one group receive the intervention and one group doesn't. So you have what's called a concurrent control. And that's generally considered a better control because you're not questioning whether conditions are different other than what you're imposing. So the data that you measure on each person are the group that they belong to. So let's say they get a particular intervention or they don't. And then you have summary data on the particular outcome. And what I'm showing you here is you have a sample size, a mean, and either a sample variance or a standard deviation on each of your groups. And so this is just a graphic of how the data might arise. So you could have a cohort study. So this is like our Framingham study. People are just observed every other year. And you might divide your participants into two groups. Maybe you want to compare men and women in each of the groups. And that would be one particular setup that would fit this analysis. Or you could have a clinical trial. And the clinical trial, you're actually randomizing participants to maybe receive a treatment or a placebo. Or they could be comparing two active treatments. Okay? And what you do is you compare the means in those two groups. So these are the formulas for a confidence interval. Again, I don't want you to obsess about the formulas. I just want you to see what's there. So if you are doing a confidence interval estimate for a difference in means, you'd start with the difference in sample means. And then you'd add and subtract your margin of error. Now, the margin of error looks much more complicated here than it did in the previous because it gets more involved. We have two samples, and we have to bring together all the information from each of those samples. But the terminology is still everything to the right of the plus minus is margin of error. You have a Z or a T score to represent your confidence level, like 1.96 for 95%, and then all the rest of it is standard error. Now, SP here, it's at the bottom, represents what we call the pooled estimate of the sample variance, of the standard deviation. So it's a pooled estimate of the common standard deviation. And all it's doing under that square root, that formula at the bottom, is it's putting together a weighted average of the two sample variances. Someone asked, what's the difference between a standard deviation and a variance? The standard deviation is the square root of the variance. We generally calculate the variance first, and then we take the square root to get back to our original units. So this SP, what it's doing is it's getting an idea of the variability in your outcome in your whole sample by looking at the variability in group 1 and the variability in group 2 and putting them together. The complexity of that formula is because we're weighting each sample by the sample size. If your two groups are equal, this becomes just a straight average. But if you have, say, 100 people in group 1 and 10 people in group 2, you'd want to count more heavily what you're observing in group 1 than group 2. Now, a few questions have come up, so before I go on, let me just answer a couple of these. In these procedures, someone asked, do we have to assume that the population is normal? You don't have to assume that the population is normal to you when your sample size is large. That's where the central limit theorem protects you. That's why that's an important theorem. However, if you get into the small sample case, now what's small sample? For a continuous outcome that's either of the groups less than 30, then you do have to assume that your outcome is normal. Another question, what's the difference between standard deviation and variance? Hopefully we just got that. One is the square of the other. Is this the paired t-test? No. We'll get to paired in a minute. This is what's called the two independent sample tests. We have two physically separate groups. When do you use the standard error? So everything here to the right of the Z or T is called the standard error. And you use a standard error versus a standard deviation. Standard deviation describes variability in observations. And so if you're trying to describe to someone how variable your observations are in a sample, you use the standard deviation. If you are trying to do statistical inference, start to predict what the mean looks like in a group or compare means, you focus on the standard error because you have to bring in the sample size when you're making these statistical comparisons. I I hope that's clear. We can come back to that if you want. So when we're doing hypothesis testing for two physically separate groups and our outcome is continuous, we want to compare means. So the null hypothesis is that the two means are equal, or another way to say that same thing is that the difference in means is 0. Those are saying the same thing. The research or alternative hypothesis can be one of these three that I've got here. You might hypothesize that the mean in one group is higher than the mean in the second, lower, or just different. Again, if we're comparing men and women, we might hypothesize some relationship between the means depending on what we think, or how men or women might respond to something. Here's a quick question. The test statistics, and then we'll go into a question. So these are the test statistics that you use. Again, Z is where you have large samples. You don't need to worry about the normality. Small samples, you should assume normality, and you use a T statistic. And here's a question for you. A clinical trial, RCT stands for randomized clinical trial, is designed to look at the efficacy of a new drug against a placebo to lower total cholesterol. What would the hypotheses be, do you think? Okay. Oh, shoot. Sorry, I went by it too quickly. So there's some differences here. So we have a clinical trial, and we want to see if the new drug will actually lower total cholesterol. So what we really want to see is the mean cholesterol for people on the new drug to be smaller than that for people on the placebo. That would be the first case. So be careful in this. A lot of you indicated in the poll that I'm seeing response number 2, because I think you saw the less than sign, but just be careful about which one is the placebo in the new. Okay, what we want to show here is that the mean in the new drug is actually lower, which is consistent with what's listed as number 1, the mean in the placebo being higher. Okay, not meant to be tricky, but just want you to be careful about which group is which. If you have a dichotomous outcome and two physically separate groups, so again, you know, a yes-no response on each person, you know what group they came from, and then you know their yes-no response. You could do a confidence interval estimate for the difference in proportions. And here's the formula. Again, this assumes that big, long mess of a formula at the top. All that's saying is it's appropriate to use this formula as long as you have at least 5 people, yeses and nos, in each of your samples. That's all that business is saying, and it's trying to write it concisely in a formula. But in English, it's just saying that you have at least 5 yeses and nos in each of your samples. If you don't make that, you use exact procedures. Now, when we have a dichotomous outcome, we can actually focus on a number of different measures. And so our dichotomous outcome follows a yes-no format. And for data analysis purposes, we often code these as 0 for the no's and 1 for the yeses. I see in that slide that probably wasn't the best way to do it, but usually we record people who give a no response as a 0 and a yes as a 1. The proportion of successes is calculated by x over n. X is the number of successes. And sometimes we call that the risk. You can also calculate an odds, which is kind of a weird quantity, but an odds takes the ratio of the number of successes to the number of failures. You see how the denominator is different? So the numerators are the same, the total number of successes. What's different is the denominator. The risk, or the proportion, is successes to everyone, whereas odds is successes to failures. Now, mathematically, these two will be similar if you have a situation where the sample size n is really large or the number of successes is really small. Numerically, these two will come out to be close in value. And you might say, well, why would you ever do an odds anyway? It's a weird thing. And I would agree with you. It's just that for some kinds of studies, you can't estimate a risk, and you have to use an odds. And you'll you do this, you'll get into this in more detail. In epidemiology, we use the case control study a lot. It's a really important study design, but we can't estimate a risk ratio. All we can estimate is an odds ratio, so it's important to know the difference between these. So when we compare two independent, physically separate groups, we really have three choices in terms of what we want to compare, and they give us slightly different information. The risk difference, or the difference in proportions, a relative risk, which is a ratio of the two, or an odds ratio, which is, again, a ratio of the proportion of successes in group 1 to the proportion of failures in group 1 to the same thing in group 2. Okay, again, if we have our way, if we can design a study prospectively and not as a case control, we could estimate a risk difference and a relative risk. And again, the risk difference is what we call an absolute measure, whereas the relative risk and the odds ratio are relative measures because they're based on ratios. And so you can calculate confidence intervals for a relative risk. You will not have to memorize this formula. I'm just giving it to you here for completeness. Or you can do a confidence interval for an odds ratio, same thing. Okay? And we'll focus on an example now in a second. And you can also do a hypothesis test. So you can either estimate, generate a confidence interval estimate for a difference in proportions, or run a test. Now, someone asked the question, sometimes when people interpret odds ratio, they say the odds are a certain number, 2.3 times higher. We will get to that, absolutely. The person raised it, it's a correct interpretation. I'll come to how you interpret an odds ratio in just a moment. So if you're interested in doing a hypothesis test and you want to compare proportions, your null hypothesis would be that there's no difference in proportions. Your research hypothesis would be that one is larger than the other, smaller than the other, or they're just different. Now, I should have said this before. We call that first option on H1 an upper-tailed test, testing if the, in this case, proportion, but it applies for means also. If the proportion is higher in one group compared to the other, we call that an upper-tailed test. The second option, where we're testing if the proportion in group 1 is lower than the other, we call that a lower-tailed test. And the last one, where we're looking for a difference, is a two-tailed test. And you might say, well, wouldn't you always know that what you were trying to find, you know, if the proportion would be higher in one group as compared to the other? And the answer is, yeah, you usually are hoping that whatever it is that you're intervening with is going to have a certain effect. You know, if you have a new drug that you think is going to reduce blood pressure or reduce, you know, something else or increase something, you would have an idea of what the direction of the research hypothesis should be. However, if you're doing a study, say for the FDA, and you've got a drug and you want to show that it's superior to something else, what they will often ask you to do is a two-sided test, because what the two-sided option does is it will give you an indication of statistical significance if your, let's say, drug is either significantly better or worse than what you're testing. Of course, you go into it hoping it's statistically better, but it might be the case that it actually is worse, and you'd want to be able to detect that. And so a two-sided test is often used even if you have a direction in mind, because one, it's harder to achieve statistical significance with a two-sided test. The bar is set a little bit higher, and it also tells you if there's a statistical signal going the other way. You wouldn't want to miss that. And so that's why people most times will do a two-sided alternative, just because it will give you a flag if there's a significant result from a statistical point in either direction. Okay? And again, here's the test statistic, and you have to have at least 5 successes and failures, yeses and nos in each of your groups. Okay, so let's get back to reality a little bit. So here's a table, and what we have here are 2 independent groups, and again, what I mean by independent are physically separate groups. So we have a group of, these are outcomes of pregnancy in women who participated in a clinical trial. Some were in the treatment group and some were in the control group. And there are just under 500 in each of the groups. And so what we have here in this table are first birth weights So those are continuous. And what are we being shown here are means and standard deviations of birth weight in the two groups. And then we have a number of characteristics. Look at all the other characteristics in the table, starting with birth weight over 4,000 grams. All the rest of those criteria in this table are dichotomous. People either meet the criteria for whatever or not. Now, with the exception of fat mass, you see the 1, 2, 3, 4th one down, that's continuous also. Okay? So the p-values over in the right side are p-values that are produced by comparing statistically whether the means or the proportions are different in the two groups. So for the first one, with birth weight, you have a p-value of 0.001. What test was used to produce that p-value? Just think about that for a second. And what the test that was used there would be the two-sample t-test. You're testing if the mean birth weights are statistically significantly different in those two groups. So it would be that test with the SP in it and the Z statistic because we have very large samples. A p-value of 0.001, is that significant? Well, if your significance criteria is 0.05, which it usually is, that would fall below, and so you'd say there's a statistically significant difference in birth weight grams between women in these two groups. Now, another important issue is clinical significance. So there's statistical significance and clinical significance. Statistical significance is determined by the p-value. Does it fall below 0.05? There are situations where you might have statistical significance and no clinical significance. And in this case, we have a difference in birth weight of about 106 grams. Okay, that's the difference if you just subtract the two means. Question for somebody in obstetrics, say, is this a meaningful difference? Is that an important amount? It reaches statistical significance, but is it clinically significant? And that's a question for someone with training in obstetrics and a familiarity with this particular outcome. Okay? So someone's writing a question, what test was used to produce that p-value? It would be a two-sample t-test, the test for a difference in means. And why weren't the variances used? The variances are used in the computation, but people will present standard deviations because they give you a feel for the variability in the groups. And now, why didn't somebody use the standard errors? I agree. They should have shown standard errors here instead of standard deviations. That would have made more sense. Now, one other thing. I'm showing you a confidence interval over on the right-hand side. I went ahead and calculated a 95% confidence interval for the difference in birth weights. The authors could have presented that confidence interval for you in this table and skipped the p-values. And the reason I made a comment, what may seem like many hours ago to you now, that said there's a relationship between confidence intervals and tests. So this confidence interval says, I'm 95% sure that the difference in mean birth weights in women who receive the treatment or the control are anywhere from, let's say, 37 to 175 grams lower in the treatment group as compared to the control group. Just looking at that confidence interval, you can make a judgment about whether there's statistical evidence of a difference. And the way you do that is you look to see, is the null value in that interval? Well, what's the null or the no difference value? Well, when you're comparing a difference or looking at a difference in means, the null value is 0. If the two means were equal, that difference would be 0. Is 0 in that interval? No. And so the test is statistically significant. Now, if you go to the next variable, birth weight over 4,000 grams, that's a dichotomous variable. The babies were either over 4,000 grams or not. About 6% of the babies in the treatment group, 14% were over 4,000 grams. The authors are showing a relative risk. That's just a ratio of the two proportions, the 0.059 over 0.143. They did it as proportions. And they're giving us a confidence interval. And in addition, they're giving us a p-value. What's the null value for a relative risk? Well, a relative risk is a ratio measure. And so the null value is 1. So 1 is not in that interval. We're saying that the babies in the treatment group are, on average, about 40% as likely to be over 4,000 grams as the babies in the control group. And we think, do we think that, it's exactly 40%? No, anywhere from 26% to 66%. But that interval does not include the null value, which is 1, and so that the difference in the proportions exceeding 4,000 grams is statistically significant. Now, if you drop all the way down to the very bottom, look at respiratory distress syndrome. The relative risk is 0.6, and the confidence interval is 0.26 to 1.67. 1 is in that interval, and so there's no statistically significant difference in the proportions with respiratory distress syndrome. And you can see the p-value is also indicative of no statistical significance. It's over 0.05. Somebody's asking, why am I looking sometimes for a 1 and a 0? You look for a 0 if you're looking at a difference measure. So when I compared the birth weights, I looked for a difference in means. So if you compare your proportions by doing a difference in proportions, you look to see a 0 in there. They did a relative risk. That's a ratio measure, so you look for a 1. Okay? Someone's asking, how do you know what test was done? Well, this is where you have to, there's actually in a way, it's sort of a system to figure out what test you do when. It depends on what does your variable look like. Is it continuous? Is it dichotomous, categorical, or time to event? And I'll explain to you time to event in just a minute. Continuous variable, you focus on mean. Dichotomous variable, you focus on proportion. Categorical and ordinal distribution. And then it matters how many groups do you have. 1 group, 2 groups, or more than 2 is essentially what it comes down to, and those dictate the procedures. Okay? We'll just do a little bit more, and then we'll take a little bit of a break. I'm sure this is getting difficult to stay with at this point. So another situation, say your outcome is continuous, and we've seen this before, but now suppose you have 2 matched samples. I showed you a moment ago 2 independent, physically separate samples, and that comes up in a clinical trial where you have people say get the treatment or get a placebo. Sometimes you have a situation where you have people measured twice, so it could be like a before and after setup. And so here's what the data look like. I'm just indicating subject ID to keep track of people, but you might have a person who you take a measurement on, you do something, you intervene, and then you take a second measurement. So here we have 2 measurements on each person. Sometimes this is called a paired sample problem, dependent or matched sample problem, same type thing. There's also a special type of clinical trial which fits this, and it's called a crossover trial. In a crossover trial, you have a group of people, you randomize them just as you would in a regular clinical trial. Some get the treatment and some get the placebo, and then after a period of time, they cross over. The people who first got the treatment, then they get the placebo, and you follow them and measure them. People who first got the placebo, then they get the treatment. So essentially you have 2 treatments on each person. So this is called a paired test, and what you do is for each person, you look at a difference score. So the little subscript D that's showing all over the place here stands for a difference score. So for each person, you calculate the difference between their first and their second measurement, and you focus on differences. And you can do a confidence interval with any of the formulas here, or you could do a test of hypothesis. And almost always the null hypothesis is that there's no difference, and the alternative could be that the difference, the change over time, is positive, negative, or just it changes over time. That would be the last case. Okay? So here's a paper that's summarizing kind of both of these things. So let me just orient you to what's here, because this is complicated, but it ties together these last 2 different types. So what you're seeing in this paper are changes in outcomes at 1 year from baseline in a control group and in a lifestyle intervention group. And this was a study done in Lawrence, Massachusetts, and it was called the Latino Diabetes Prevention Project. So what we have are two groups. Some people got a control and some people got an intervention. So the intervention effect column, if you see that, which is over on the right-hand side, is comparing the two groups. So all of the analyses in that column are basically comparing two independent groups. So the p-value and those confidence intervals. Now some of you are asking, I don't know if I should be looking for 0 or 1. Anytime you have a confidence interval, if it's a confidence interval for a difference in means or a difference in proportions, you look to see is 0 in that interval. Because if it's a difference measure, then the no difference value is 0. So if you scan down that intervention effect column, every confidence interval that does not include 0 has a p-value over in the right that is significant. Okay, so the first one is comparing changes in weight between the control and the intervention people. And the difference in the changes is about 2 units. The confidence interval does not include 0, so the p-value is significant. Go about halfway down the table and look at fasting blood glucose. And the participants who are in the control group, they dropped about 1.5 units from 1 year to baseline. Versus people in the intervention, they went up 0.5 units. Actually, it should be the other way around. The control people went up 1.5 and the others dropped because it's a change at 1 year from baseline. The difference between them was 1 unit, but do you see the confidence interval includes 0? So we can't say that there's a statistically significant difference in the change in fasting blood glucose between the two groups. The p-value is 0.62. The confidence interval includes 1. Okay? It includes 0. I'm sorry. There are lots of questions popping up. I apologize. They're popping up on my screen, so I'm trying to respond to those as I'm saying these things. All of the confidence intervals on this table are confidence intervals for differences in continuous measures. So we're always looking to see is 0 in that confidence interval because we're looking at a difference measure. All right? And the p-values on the right side, the ones that are not significant, you'll see, coincide with the ones that include 0. The p-values that are significant, below 0.05, correspond to confidence intervals that do not include 0. They're either all positive or all negative. Now, someone says, can you repeat what you said about choosing a test? This is important, okay? So this is a big picture issue. How do you know what test to use when? And I've got some practice questions on this that are going to come up in a minute, so we'll maybe take a break and get to those. But before we stop, how do you choose what test to do when? Here's what you have to think about. What kind of an outcome do I have? Continuous, dichotomous, categorical, and it really doesn't matter to differentiate categorical and ordinal because the procedures are similar, but categorical, ordinal, or time to event, and I'll explain to you time to event in a minute. So what's the type of variable that you have? Then how many groups do you have? Is it just one group and you're comparing against a historical value? Do you have 2 concurrent groups, like a clinical trial? Or do you have the matched paired type thing, before and after? Those are the types of questions that you have to ask, and they dictate the type of test that you use. Now, someone asked the question, if you do a matched design, does that change your likelihood of making a type 1 error? No. You have the same kind of probability for making mistakes. What really dictates these probabilities of errors are the sample size. You have a large sample that will ensure that you are more likely to make the correct decisions. One last slide, and then we'll take a break and come back and practice some of these things. So I'm saying the p-value and the confidence interval can get you to the same place essentially. So if you look at a confidence interval, you can make a judgment about statistical significance. And that's that very last line on this slide. If the null value is included in the interval, then there's no statistical significance. Now, what's the null value? It's a 0 if you're looking at a difference measure. It's a 1 if you're looking at a ratio measure. So why would you need both then? Well, the confidence interval can only give you an indication of whether you have statistical significance, yes or no. The confidence interval gives you an idea of the magnitude of the effect. The p-value tells you just how significant things are. Okay? So they both are important. They give you different information. If you just want to know, is there a statistically significant difference, then just do a confidence interval, because you can make that judgment, and you get a bit more in the magnitude of effect. If you want to know how statistically significant is your data, then do a test of hypothesis, and your p-value will summarize exact significance. This is difficult, and I know I'm giving you a lot here in a short period of time. It takes some digesting. So the next set of slides do have some practice questions on this. So what I'd like to suggest is we take maybe a 5-10 minute break. I'll give you a chance to run to the restroom and get a drink of water, and then we'll come back. I'm going to put my telephone on mute just for a minute, but I will come back very shortly. Okay, so we'll just take a quick break and come back and do some practice with this. All right? Thanks. Okay. I hope people have a chance to take a short break. Whoops, didn't mean to do that. Let me go back. Let me just answer a couple of questions. Some of you are raising some excellent questions right now, and I want to make sure we go through them. So first of all, someone says, what if you have a confidence interval for a relative risk and it includes 1? What that would mean is that you wouldn't be able to reject the null hypothesis. That's absolutely correct. And then the person goes on to say, so does that mean you could say that the risk of whatever your outcome might be is the same in the two groups? Now, this is really important. I'm glad you raised the question that way. So when you set up a test, your null hypothesis, say, is that the risk of developing a certain outcome is the same in two groups. If you do a confidence interval estimate for the difference in risk, and that confidence interval for the difference either includes 0, or the confidence interval for your relative risk includes 1, and by the way, they'll be consistent. You know, if the confidence interval for the relative risk includes 1, then the confidence interval for the risk difference will also include 0. All you can say there is that there's no evidence of a difference in risk. You are not proving that the groups have equal risks. This is really important. So remember that weird slide that I had way back that had the different types of errors? If you don't reject HO, you are not proving that the null hypothesis is true, because it's very possible that you're committing a type 2 error. And so when you don't reject the null hypothesis, while it might be the case that there's no difference, you don't know that. And so all you can say is that either you have statistical significance because your confidence interval does not include the null, or you don't. You're not proving the null to be true. This is really important, and a very important question. I'm glad that you raised that one. Someone asked, can you re-listen to this webinar later on? Yes, you can download this and you can listen to it as many times as you feel like you can take it. And then someone says, when in journal articles, should authors be showing standard deviations or standard errors? They really should be showing standard errors. Now, let me take that back. When people put together, say, a table 1, in a table 1 of a paper, they're often describing to you the characteristics of the participants. In a table 1, that's where you want to see means and standard deviations. You want to see what does the average age look like of the participants in the sample, what's their height and weight if that's relevant, things like that. So there you'd see means and standard deviations. When they get to reporting on outcomes, when they're estimating what's the mean, cholesterol level, because that was the primary outcome, that's where you want to see means and standard errors, or means and confidence intervals around those estimates in your outcomes tables. I hope that makes sense. Okay, so we'll keep going and keep the questions coming, and I'll try to answer them as we go along. All right, so just a few practice. These are questions that were some of you were raising. The null value of the difference in means is what? And we can go through these quickly. It should be 0. Now, some of you are saying 1. 1 is the null value for, think about it. If you're comparing two things, you can either compare them by taking a difference between them or computing a ratio. If the two things are equal and you compute a difference, then the no difference value would be 0. If you have two things and they're equal and you compare them by a ratio, then the no difference value would be 1. So that's the distinction. The null value of a mean difference. This one would also be 0. Now you might be saying, didn't you just ask me that? The language is very subtle and different. The last slide said a difference in means. This says mean difference. And someone just said you didn't change the slide. I did. And the last one said difference in means. That's when you have two physically separate groups. Mean difference is when you first compute difference scores on people, and then you take the mean of those. You do a mean difference when you have a paired sample design. Okay? And again, because it's a difference score, though, 0 is the null. Null value of a relative risk. Good. A lot of you are saying, yeah, a relative risk is a ratio, and so that would be 1 would be the null value. Null value for a difference in proportions. Again, even though we're talking about proportions, you can look at a difference in proportions, and the null value of a difference would be 0. Odds ratio. Good. I think most of you got this one. Our odds ratio is also a ratio measure, so the null value is a 1. Good. A two-sided test for the equality of means gives you a p-value of 0.2. Say you do it in a statistical package or you read it in a journal. Would you reject the null hypothesis? In other words, find that to be statistically significant? Good. Almost all of you are saying no. That's good. And it only would be if you felt like your significance criteria was above that, but almost always we use something like 0.05, even 0.01, and that would not fall below those values. Okay? So again, if this was the case, we would not conclude, based on this result, that the means are equal. We're not proving the means to be equal. We can't say that they're different. And I know that sounds funny, but you can't say they're different. Now, someone says, why isn't the answer to this question maybe? It does depend on alpha. You are right. It does depend on alpha. I'm assuming that your alpha would never be above 0.2. You'd never set up a test with a more than 20% likelihood of committing a type 1 error. So, you know, technically you are right, but I don't think it would be a realistic setup. Okay, so analysis of variance. So this is, again, don't worry about the formula so much. I just want you to get big picture. When you're doing hypothesis testing and you have more than 2 groups, then the analysis, if it's a continuous outcome, would be done by analysis of variance. So this is an extension of the 2-sample test for means. It's just you're moving beyond the 2 groups. Now the formula gets complicated because for each sample, each group, we have a sample size, we have a sample mean, we have variability, so it does get quite complicated when you do these formulas. But analysis of variance is a technique that's used to compare more means of a continuous outcome in more than 2 groups. Okay? And when you do an analysis, I suspect many of you have seen results, you set up what's called an analysis of variance table. And the analysis of variance table essentially breaks apart the components of the statistical test. And when you fill in all of these numbers over on the right-hand side, you get your F statistic, which is just your test statistic. Now, just a couple of big picture issues. When the sample sizes are equal, a design is said to be balanced. All it means is you have, roughly equal, you have equal numbers in your comparison groups. And if you have control over this, balanced designs are desired over those with unequal sample size. Now, sometimes you don't have control, but if you are designing a study and assigning people to the different groups, assign them in equal numbers, because balanced designs give you higher power. What that means is a lower probability of a type 2 error, or in other words, a higher probability that you'll reject the null hypothesis when it's false, and are more robust to violations in assumptions. What that means is, even if your data don't quite meet normal distributions and you fall below the sample size of 30 in each group, if you have equal sample sizes, that gives you some protection against the violation of assumptions, and things will work out from a statistical standpoint if the sample sizes are equal. You don't need to know, again, on this last slide, you don't need to know all of these technical details. I just want you to have the formulas. If you've done a lot of these calculations in your history, what you need to know, big picture, when would you use an analysis of variance? It's applied when you have more than 2 independent groups and you have a continuous outcome. If you have, again, a continuous outcome, often with more than 2 groups, often you have, let's say you have a clinical trial, you randomly assign people, and you have a control group, you have a group where people get your new drug, and then you have a third group where people get a standard drug. Sometimes it's not just a placebo versus your drug. Maybe it's placebo, your drug, and what's currently available. Maybe there are 3 treatment arms. Maybe there are even 4 or 5. So once you get past 2 groups, it's analysis of variance with a continuous outcome. If you run your analysis of variance and you find statistical significance, sometimes it's then of interest to make specific comparisons after the fact. So you do what's called an overall test, the analysis of variance test, and your conclusion is that the 3 means are not all equal, or the 4 means are not all equal. Then you can compare, well, is my drug different than placebo? Is my drug different than what's currently available? Those are called multiple comparisons. There are a series of tests that are kind of done after you do the global assessment to make specific comparisons. And I'm just throwing up some terms here. Maybe you've seen them. There are different procedures that you can use, a Tukey test, a Chaffee test. They often are named after people, and they are just tests that are used to make specific comparisons. And you might say, well, you already showed us how to do a 2-sample t-test. Why couldn't you just do a whole bunch of those if you wanted to do comparisons 2 at a time? The problem comes in, every time you do a test, you set a level of significance, say 5%. And you can, so that means that there's a 5% chance that you'll find something to be significant when in reality it isn't. That's your false positive. Well, these multiple comparison procedures control that type 1 error rate over a series of tests. And so what they do is they kind of set the bar higher so that over a series of tests, it protects your type 1 error rate. Now, another test, another option here is to take your 0.05 and divide it by the number of tests. That's called a Bonferroni correction. Some of you may have seen that in the past. That's another approach. It's a very conservative one, but it's a certainly fine approach. Higher order analysis of variance, there's such a thing as 2-factor analysis of variance, 3-factor analysis of variance, and so on. What this is say we have our clinical trial and we've got some people in a control group, some are getting our new drug, and some are getting a standard drug. So that's 1 factor, the treatment, and there are 3 levels of treatment. We might also have an inkling that the drug is differentially effective in men versus women. So another factor might be the sex of the participants. We would analyze whether there's a drug effect, a sex effect, or some combination. And that would be done with what's called a 2-factor ANOVA. So the drug effect would be important, the sex of the person would be important, and then whether there's any interaction between those 2 or a combined effect of those things. Again, just the terminology, big picture. Obviously, you could do a whole course in that idea, but this is just big picture. And then last idea or extension of this, there's something called repeated measures analysis of variance that extends that before and after type thing where you do the paired t-test. Some of you raised a few questions. The paired t-test is when you have exactly 2 measurements on each person, maybe a before and after, and that's where you look at a different score. So that's the paired t-test. But suppose you have a baseline score, a measure at 12 months, a measure at 24 months, 36 months. Once you get past 2 measures, you can't really calculate 1 different score because you're taking repeated or serial measures. You analyze that with what's called repeated measures, and you look to see, is there an effect over time? And that's done, again, with analysis of variance and some of the details there, but it's called repeated measures analysis of variance. One more test Suppose you have multiple groups. Again, maybe you are 3 groups, but your outcome is not a continuous one, but it's dichotomous, ordinal, or categorical. This you would do with what's called the chi-square test of independence. And the data setup is often like this. So you'd have what's called, we call it sometimes an R by C table, so a row by column. So this would be a 3 by 3 table. So say you have 3 treatment groups, A, B, C, and then your outcome, it could be just 2 levels, or it could be 3, or even more. But if you can organize your data into a cross-tabulation table like this, then you are likely to analyze whether there's a statistically significant difference in the outcome by the groups with what's called a chi-square test of independence. And what I'm trying to show you here is when you do the analysis, you'd have counts, numbers of people in these cells. But what I did was in group A, I figured out what percent have outcome 1, what percent of outcome 2, and what percent of outcome 3. So in group A, most of the people are in outcome categories 2 and 3, and then fewer are in category 1. Notice that they sum to 100%. For B, most of the people get outcome category 1, and then they're evenly split in 2 and 3. For group 3, almost everyone got outcome category 1, and then a little bit in 2 and 3. So the question that you'd ask here is group assignment related to outcome? Is there a different distribution of the outcome by group? And in this particular layout, your answer would be yes. People in group C are much more likely to have response 1 than anybody else. Now, someone wrote up, why wouldn't you do this as an analysis of variance? Well, analysis of variance, you're right, is multiple groups, but the outcome for analysis of variance is continuous, not categories. So analysis of variance, you might have group A, B, C, but your outcome would be continuous, and you'd essentially have the mean for group A, the mean for group B, and C. Okay? So here's a paper, and what this is showing is a table 1, demographic data, and you see some statistics. This, again, I do happen to do work in obstetrics a little bit, and so this is 2 categories, 2 groups, women getting treatment, weekly courses of antenatal corticosteroids and single courses. And what we have are some data on the participants at baseline. So let's just take gestational age at randomization. That's the second line in the table. And what we have are means and standard deviations. And standard deviations, by the way, are appropriate here to just describe what the participants look like in terms of their gestational age. And so the p-value on the right side, 0.13, and I'm looking at the second row down. Think about this for 1 second. What test was done to generate that p-value? And so again, here's what you have to think. What kind of measure is gestational age? Well, it's the number of weeks of pregnancy, and so it would be continuous. People could have, 14 weeks gestation all the way out to, 37 weeks gestation. So it's a continuous measure, 2 physically separate groups, so this is a 2-sample t-test. Is there a statistically significant difference? No, because the p-value is 0.13. Now, would this be a paired t-test? The answer would be no. Paired is when it's the same people measured twice. In this study, and I know I'm not giving you all the detail, but in this study, women got either a weekly course of treatment or a single course, so they're different. Now, why aren't they showing standard errors? Because this is just this table here is trying to describe the demographics of the participants. We're not trying to make any inferences. We're just trying to describe gestational age and other characteristics of the mothers. So the statistical test is the 2 independent sample t-tests. That's correct. What test was done to compare race ethnicity between the 2 groups? The p-value of 0.74. Where did that come from? Now, a number of you are responding here. Well, what kind of variable is race ethnicity? That's a categorical variable. So if you can think of pulling that race ethnicity piece right out of the table, that looks like that table I just showed you. So it would be a chi-square test of independence. Okay? Now, another point was raised, if you're just trying to describe the two groups and give the reader a feel for, what the people in the weekly course got from those in the single, this is a clinical trial. You wouldn't expect any of those p-values to be significant with randomization. In fact, most journals will tell you don't even show them because you're not doing statistical testing here. You're just trying to give people a feel for whether the randomization was successful. So I wouldn't even show those p-values at all. So I'm hoping you're getting the feel for this a little bit. Let me give you a few more practice problems and see if you're feeling comfortable with it. So in the Framingham study, we want to assess, say, risk factors for impaired glucose. So let's suppose we look at an outcome of glucose category. And what we do is we classify people as having diabetes if their glucose is greater than or equal to 126. We call them impaired fasting glucose if they're between 100 and 125, and we call them normal otherwise. Okay, that's our outcome, the 3 levels. And we're looking at several risk factors: the sex of the person, their age in years, and BMI, which we're categorizing as normal, overweight, or obese, and their genetic disposition. And let's suppose they have a particular genetic risk factor or not. All right? So what test would you use to see whether sex was associated with glucose category? Okay, a lot of you are responding. Good. It would be the chi-square test for independence. Why? Because the sex is 2 groups and glucose category is 3 groups. So what you would do is you'd set up a 2-by-3 table. The sex as the rows of the table, male, female, and then the columns could be the glucose category. Why not goodness of fit? And someone asked me that. Sorry, I missed that a minute ago. There's the chi-square test of independence and the chi-square goodness of fit. Chi-square goodness of fit is used when you have only one study group and you're comparing against an external distribution. Okay? So here we're comparing men and women on the glucose category. If we, for example, had data from another cardiovascular epi study that told us X% were diabetic, X% impaired, X% normal, how does Framingham line up against that? That would be goodness of fit. But here we're comparing men and women on this. Why is this not analysis of variance? Because our glucose category, we're not analyzing the continuous glucose measure, we're putting people into categories. How about this one? How would you test whether age was associated with glucose category? Good. A lot of you are getting this. Analysis of variance. Here, age is continuous. We have 3 glucose categories, and what we have is continuous ages. So we look at mean ages in the 3 groups and compare them statistically. Good. What about BMI? Now, think about how BMI was operationalized here. BMI and glucose category. Okay? So this one would be chi-square test of independence because we put BMI in categories, normal, overweight, obese, and glucose category. So here you'd have a 3-by-3 table. Okay, so now let's change it up a little bit. Let's take the outcome and look at fasting glucose level as it is. Okay, so we're measuring people's glucose levels and not putting them into groups. Same risk factors. How would we test whether sex is associated with glucose level? Okay. So this would be a test for equality of means because glucose level is now continuous, and we have two groups, men and women. Okay? Now, some of you are saying ANOVA. You can do ANOVA with two groups. I usually think of doing the t-test for a difference in means just because it's easier. But ANOVA is mathematically equal to that, so that would be okay too. How about BMI and glucose level? Again, think of the way we put BMI into the mix for this. Okay? So this will be ANOVA. Good, because BMI is categories and glucose level is continuous. Good. It's not chi-square because the glucose is continuous. So once you have one continuous, you have to look at means somewhere. Either equality of means if it's exactly two groups, or ANOVA if it's more. Age and glucose level. Okay, this one a lot of you are saying, I don't know, and that's right. Age is continuous, as is glucose. Someone said the answer here. We'll get to it in a second. So this would be with a correlation or a regression analysis. Okay, well, I'll explain that to you in just a minute. A couple more. Let's say we had a third outcome, a different outcome, and it was diabetes, yes or no. Okay, so our outcome is diabetes, yes or no, and same risk factors. How about sex and diabetes? Good. Chi-square test of independence. A lot of you are saying that now. So here we'd have sex, male, female. Think of putting together, it would be a 2-by-2 table. So male, female as the rows maybe, and diabetes, yes, no as the columns. BMI and diabetes. Don't forget how BMI is measured here. BMI is the categories, normal weight, overweight, obese, and diabetes. So here we'd have a 3-by-2 table. Excellent. A lot of you are really getting this. Age and diabetes. This is the last one. Okay? Yeah, so this is, so age is continuous, so we definitely want to focus on means, and diabetes is just 2 levels, so you could do it as equality of means, and you can definitely also do it as ANOVA. Some of you are saying ANOVA. Again, I think of doing, a test for means. It's just a little bit easier to manage, but mathematically they're equal. So some of you are asking, can we look at this later on to go back over it? Yes, these slides are in the set, so you can see these if you want to hash through some of this some more. Okay? All right, so let me go on to the last little bit here, and I know it's going long, but we'll try to get through a bit more. So correlation and regression. So correlation and regression analysis are used when you have 2 continuous measures. So that question that I asked you a minute ago about how would you relate age and glucose level, I said other. It would have been done with correlation or regression. So we look at correlation and regression when we have 2 continuous measures. So correlation looks at the nature. What I mean there is direction, positive or negative, and I'll explain that to you, and strength of the linear association between 2, I should say, continuous variables. And in regression analysis, this is related, but instead of looking at just the direction and the strength, we actually spell out the equation that best describes the relationship between these 2 variables. So a correlation can be positive or negative, and a positive means that as one variable increases, so does the other. A negative relationship means as one variable increases, the other goes down. So they work in inverse. Okay, and so if you saw this kind of a diagram, now this is called a scatter diagram, so the x variable is on the horizontal axis and the y is on the vertical. Now x is usually called our independent or predictor variable, y is the response or the outcome variable. If you saw something like this, this would produce what a correlation equal to 0. And what a correlation of 0 indicates is that there's no linear association between these two variables. So when you see something like this, it's just a random scatter, you can't predict y from x. A line does not well describe this association. Okay? What about this particular relationship? So this is an example, again, where the correlation would be 0, even though there is an association between x and y. It's just not a linear one. And so the correlation, R, gets at the nature and strength of the linear association between two variables. Okay, so a line doesn't describe this association. It's actually well described by a curve. So a linear relationship, if you looked at a scattering of points, maybe they cluster bottom left corner up to the bottom right. That would be a linear relationship and positive. Now, in regression analysis, we take our variables. Again, y is the dependent or outcome variable, x is the independent or predictor, and we come up with the equation of a line. And y with a little hat over it just stands for predicted value of y. And we relate x to y with the equation where b0 is the y-intercept and b1 is the slope. And the way you interpret those is this. So the y-intercept is the value, or the predicted value of y when x is 0. We usually don't care that much about the y-intercept. We care more about the slope, because the slope gets at the real association between x and y. The slope is the change in y relative to a 1-unit change in x. And so if you change x by 1 unit, y will change by b1 units. And so that's what we usually care about. And you can, with statistical tests, determine whether there's a statistically significant association between x and y by testing whether the slope is statistically significantly different from 0. Because if the slope were 0, that would say there's no association between x and y because you're multiplying it by 0. But if the slope is statistically significantly different from 0, then there's an important relationship between x and y. And the sign and magnitude of B1 tell you just about how strong and the nature of that relationship. Just like with other statistical tests, there are some assumptions. The assumptions for linear regression, now I'm calling it simple linear regression, not because it's easy, but we use the term simple when we have exactly one predictor variable x and one outcome variable y. And linear is that we're assuming that a linear relationship describes, or a line describes the association between x and y. We assume independence of errors. What that means is you have a sample of individuals who are unrelated. So if I had 100 people in a sample and I was trying to understand whether there was an association, let's say, between number of hours of exercise and blood pressure, if I had 100 people, I would want to be sure that they were 100 unrelated individuals so that there isn't something genetic that factors into the association. Homoscedasticity, what that means is that the variability in the outcome, y, is constant across the value of x. So you want to be sure when you look at a scatter diagram like those plots I was showing you before, that the picture doesn't look like it fans out. Say, it starts where points are all clustered together and then they fan out. You want there to be sort of a constant variability in y across the range of x. And we also assume that the outcome y is normally distributed approximately for each value of x. There are statistical tests that can test whether these assumptions are reasonable or not. This is getting much further beyond what would be considered the core issues of biostat. But you can go into lots of depth with this. Multiple linear regression is used when you have a set of predictor variables. So you have a set of x's, and you want to relate those simultaneously to some outcome. So let's say our outcome variable is blood pressure. In the simple linear regression case, we might want to relate number of hours of exercise to blood pressure. That's a simple linear regression where you have one predictor, exercise, and one outcome. Well, there are lots of things that are related to blood pressure, and we might want to evaluate them simultaneously. So we might look at exercise, we might look at age, we might look at whether a person smokes. All of those at the same time, and you could do that in what's called a multiple linear regression. Sometimes people call this multivariable regression. You might see that in papers. This is not multivariate regression, although people use that term incorrectly a lot in the literature. Multivariate is used when you have multiple outcomes at the same time, and usually people don't mean that. So usually people are doing what's called a multiple linear regression or a multivariable regression, like what you're seeing here. Simple regression is used, but it's not used all that often because there are usually lots of things that affect an outcome, and we want to evaluate them simultaneously. Oh, I should say, the way you interpret these parameters in the model, so B0, it's not exactly the y-intercept anymore. It is the value. It's the value of y when all the predictors are equal to 0. And then the regression coefficients, B1, B2, all the way down the line, those still represent the change in y relative to a 1-unit change in, let's say, x1, holding everything else constant. Okay, so sometimes people talk about these regression coefficients as measuring the change in the outcome by represented by a 1-unit change in the predictor, adjusting for the other variables. Sometimes you might see that term. If your outcome is repeated, you do a different analysis. This is measuring the outcome one time on each person and measuring each of the predictors one time. Okay, if you have repeated assessments of the outcome, you have to do a repeated measures analysis. In the multiple regression case, the model, the parameters are really called conditional, meaning that they are after accounting for all of the other things. So that's where, when you interpret them, you say adjusting for these other variables or holding the other things constant. And when you have a multiple regression equation, you usually do an overall test and you see, does this set of variables, is this set of variables statistically significantly associated with the outcome? If the answer is yes, then you can dig deeper and say, okay, which ones are important and which is the most important, what's the next most important? And the way you judge relative importance is by p-values. You can't just look at the magnitude of the regression coefficients because your predictors are usually measured on different scales. You might have age in years in the model. You might have the sex of the person, which is a yes-no, female sex, male sex. You might have number of hours of exercise measured in hours per week, and so on. You can standardize all of your variables so that they're all on the same scale. People tend not to do that. Instead, they look at p-values to judge the relative importance of the variables because those are all on the same scale. Now, for multiple linear regression analysis, the outcome is continuous. The predictors, though, can be either continuous, like age, indicators, like sex, or a set of dummy variables. Now, dummy variables are a set of variables that you use to represent a categorical or an ordinal predictor. So let's say, for example, you wanted to put, our outcome was blood pressure, and we wanted to model the age, the sex, and the race, ethnicity of the person. Well, age goes in as a continuous variable. The sex, you'd have to code men or women as 0 or 1 and the other as the opposite. Okay, that's fine. But then let's suppose we have 3 race ethnicity groups, white, black, Hispanic. I know there are many more, but let's just make it simple for this. You can't put in a variable that's coded 1, 2, 3 because the analysis, the computer will assume that that's an ordinal variable and 2 is higher than 1 and 3 is higher than 2. What you have to do is you create 2 dummy variables. If you have 3 categories, you need 2 dummy variables. If you happen to have 4, you need 3. The reason you need 1 less is this. What you do is you choose, out of those 3 different categories, you choose one group to be the holdout or the referent group. It doesn't matter which one you choose, you just have to pick one. So let's suppose I choose white race as the holdout or the referent group. Then what I do is I create 2 indicator variables, and they're each 0, 1 variables. So if a person is of black race, they get coded 1 on the black variable and a 0 otherwise. If a person is of Hispanic race, they're coded 1 on the Hispanic variable, 0 otherwise. Now, why don't you need an indicator of white race? Well, if you have these 2 variables, black and Hispanic, if someone is 0 on the black variable and 0 on the Hispanic, that means they're white. So that's why you don't need a 3rd variable, because it would be redundant. Okay, so then you put in the black and the white indicator variables in the model, and then you can interpret the coefficients associated with those, and they tell you how blacks differ from whites in terms of the outcome, Hispanics differ from whites. So you have to think about the kinds of comparisons that you want to make, and then you set up your dummy variables accordingly. Now, these are 2 huge topics that you would talk about extensively in epidemiology, confounding and effect modification. But these are issues that we often evaluate or investigate with multiple regression analysis. One is confounding, and that is really the distortion of the effect of a risk factor on an outcome by other variables. Maybe we really want to look at the association between exercise and blood pressure. Well, we could do a simple linear regression and just put exercise in as our predictor and blood pressure as our outcome. Well, lots of things are associated with blood pressure, and we wouldn't want to attribute a big effect to exercise when it might be different things. Well, what age is related to blood pressure? Age is also related to exercise. As you get older, you can't do as much vigorous exercise as you might do it when you're younger. So if we don't account for other variables, we can either over-attribute an effect to a variable or maybe miss it. It could be due to other things. Or we might not see an effect, but that's because other things are masking it. And so you can use multiple regression analysis to address confounding. Effect modification is a different concept, and this comes about when we have a different relationship between our risk factor and our outcome depending on another variable. So it's not confounding, but it's actually a different relationship. Let me try to show you, illustrate that with an example. It might be clearer because it's hard to grasp that idea. First, though, let me show you an example of confounding. Let's suppose that where our outcome variable is systolic blood pressure, and we have 4 variables that we're putting in as potential predictors. Age of the person, sex of the person, and I'm just coding males as 1 and females as 0, and BMI, and let's suppose we use it as continuous, and whether people are taking blood pressure lowering medications. A couple of you are asking me, is effect modification statistical interaction? Yes, same thing. On the left-hand side of this slide, I have 4 simple linear regression models. And what I did was I related each of those predictors, one at a time, to blood pressure. So in a simple linear regression model relating age to systolic blood pressure, age was significant, and the slope coefficient was 1.03, meaning each additional year of age was associated with a 1.03 increase in systolic blood pressure, and that was statistically significant. Male sex was also statistically significant with a slope of minus 2.3, meaning that men, on average, had blood pressures about 2.3 units lower than women. That's also statistically significant. Now let's just go down to the blood pressure meds variable. People on blood pressure meds, on average, had blood pressures 34 units higher than people not on meds. Now at first, sometimes people look at that and they say, that's weird, why would they be higher? Well, they're higher because their blood pressure is so high, they need meds. Okay, so it is higher for those people. So now the question is there any confounding? Is there any confounding in this association between blood pressure meds and systolic blood pressure? So the right-hand side of this slide is the result of a multiple regression equation where I have one equation and I've entered into it as predictors age, sex, BMI, and blood pressure meds all at once. So now notice that the regression coefficients, the slopes change a little bit because each of those now is estimated in the presence of the other variables. So what's happened now to the association between blood pressure meds and blood pressure? It's actually gone down. And so what's happened is in the simple linear regression model, we're saying that there's a real huge effect, about a 33-unit difference in systolic blood pressure for people on versus not on medications. Well, now when we're adjusting for age, sex, and BMI, that effect is reduced. That's because there is some confounding due to age, sex, and BMI. Now, there are statistical tests to judge confounding. There are also other approaches, and one is sometimes people look to see how much does that coefficient change. And sometimes people look and see if that coefficient changes by more than 10%. And in this case, it does. There's actually quite a substantial difference in the association between blood pressure meds and outcome when you adjust versus don't adjust for the other things. So this would be evidence of confounding. Okay? Here's a little table that summarizes the results of a clinical trial. And this trial was designed to evaluate a new drug as compared to placebo to raise HDL. HDL cholesterol is your good cholesterol, so higher is better. And what you see here is among women, there was really no difference. Look at the mean values for women. So among the women, nothing is really happening at all with HDL. However, among the men, those who got the new drug had much higher HDL levels than those who got placebo. So this is an example of an interaction between sex and drug or effect modification by sex. There's no association, no difference, no impact of the drug among women, but there is an impact among men, a different effect. So this is what's called interaction or effect modification. Okay? So now let me just shift over to logistic regression. So linear regression is used when your outcome is continuous. Okay? Linear regression is for continuous outcome. Logistic regression is used when you have a dichotomous outcome. All right? So rather than your outcome being systolic blood pressure, your outcome might be hypertension, yes or no. Okay? And so once again, we want to relate one or a set of predictors to an outcome. So simple logistic regression relates one predictor to a dichotomous outcome. Now you can look at these equations, you might say they don't look simple at all because things have to get more complex when you have a dichotomous outcome. So the equation to relate the probability of having the outcome, that's the p hat, to the predictor is that complicated ratio in the middle of the slide. All that manipulation to get to the bottom line on this slide gets the right-hand side of the equation looking more like the multiple linear regression equation. Okay? So the left-hand side of the equation is the log odds of the outcome. Sometimes that's called the logit. So the log odds of the outcome gets us to the more familiar regression type equation on the right-hand side of the equation, which people tend to be more familiar with. The multiple logistic regression model, again, has a dichotomous outcome, but we have more than one predictor on the right-hand side. Now, how do you interpret these regression coefficients here? So B1, B2, all the way down to BP, if you look at any one of these represent the change in the log odds of the outcome relative to a 1-unit change in the predictor. Well, that's hard to digest. What is the log odds? So what people tend to do is they exponentiate those betas. If you take the exponent of those beta coefficients, you get odds ratios. Someone raised this question a while back when we were talking about odds ratio. So let me show you an example. So here's the result of a multiple logistic regression relating birth defects, yes or no, that's our outcome, whether the child has a birth defect, to whether the mother smoked in pregnancy, yes or no, and the mother's age in years. Okay? So this is a multiple logistic regression because the outcome's dichotomous and we have more than one predictor. So a statistical computing package would spit out those beta coefficients, the B's. And then there are p-values. So first looking at the p-values say that smoking is not statistically significantly associated with birth defects adjusting for age. Age is statistically significant. The p-value is 0.04 after adjusting for smoking. Now to interpret those B's, what we do is we exponentiate. All right, so if you take the exponent of the EXP on your calculator, 1.062, you get 2.89. And the way you interpret that is mothers who smoke have almost a 3 times the risk of having a baby with a birth defect than mothers who don't smoke. I hope that makes sense. Okay? Now, notice that confidence interval for the odds ratio around the estimate for smoking. It includes 1, which means it's not significant, and that's justified by the p-value. And I should say adjusting for age. Thank you. Okay? So the risk of a birth defect is almost 3 times higher in mothers who smoke versus mothers who don't, adjusting for age. That is, however, it seems like a large effect, and it is. It's not statistically significant. Now the age variable. If we exponentiate the 0.298, we get 1.35. The interpretation is the odds of having a birth defect when you compare 2 mothers who differ by 1 year in age is about 1.3 times higher for the mother who's 1 year older, adjusting for smoking. And the confidence interval does not include 1, so that's statistically significant. Okay? Oh, what happened? Sorry. Okay. Okay, one last concept, and this is survival analysis. And again, big picture, you can do whole courses in this. Some intro courses don't get to this, but many do, just to give you the flavor and, again, how this fits into things. So just context. Linear regression is for a continuous outcome. Logistic regression is for a dichotomous outcome. Survival analysis, we look at time to event. I've missed a slide here because I jumped forward. The outcome is time to an event. So it's not just looking at whether a person has a particular outcome, yes, no, it's when did that outcome come, okay? And so it's like you almost have 2 outcomes, whether they developed an outcome, yes or no, so that's a dichotomous, and the time at which that happened. So it almost combines the previous 2 topics. And one of the features of survival analysis is that you have incomplete follow-up information. Usually we do survival analysis where our data is collected over a period of time. We have a starting point, and people come in. They're actually often recruited into a study over months or years. And then you follow them up till the time they develop something or until the end of the study. The study could go 5 years, 10 years. So for some people, the study ends before they actually develop the event. So all you know about them is they were in the study for 5 years, and they were event-free. And so you use that information. We don't know that they would have never developed, but what we know is they had 5 years of event-free time. And so we use that information. And there are a number of statistical tests that can be used to compare things, but the first thing we often do is put together a survival curve. So you might see a curve like this, and again, there's a lot behind this, but I think based on knowing some of the things that we've talked about today, the time is on the x-axis, and the probability of survival is on the y-axis. Notice at time 0, that curve should connect to 1, because everyone is alive at time 0. So then the survival curve drops down as time goes on. If a survival curve drops very sharply down, that means that the survival, really drops off very quickly. If the curve stays close to the top, of this graph and goes out long and flat, that means there's very good survival over a long period of time. Usually two things are of interest in a curve like this. You could estimate what's the probability someone would survive, say, 2 years or 5 years or 10 years. So I've illustrated here the survival probability for 2 years is 83%. So the way you find that is you look at 2 years and you go up and read over to the left. So the probability that someone survives 2 years is about 83%. You can also look at median survival, and you could say, how long does about half the sample survive? So to figure out median survival, you first find the 50% point on the y-axis, and then you read to the right and down. And the median survival is about 11 years. Okay? You can compare survival. You can do clinical trials where your outcome isn't something continuous and isn't something dichotomous, but maybe it's a time to event variable. So this is a clinical trial where some people got chemotherapy before surgery, some got chemotherapy after, and the outcome was actually mortality, and people were analyzed up to about 4 years. So you can see that those who got chemo after surgery have better survival. Their survival curve is much higher and up to the top, whereas people who got the chemo before surgery, their survival declines more sharply. You compare these two things, it ends up being a chi-square test, which is along the lines of the chi-square test we talked about before, but it has built in a few little wrinkles here to compare these. But you could, I think, based on what we've done so far, look at these curves, see a p-value of, a p-value, and determine whether you can reject HO, which is equal survival. You can also do regression type models for survival, and I should say I'm using survival and talking about the outcome being mortality. It can be timed to anything. So it could be timed to developing heart attack, and people survive heart attack. It can also be timed to a good outcome, timed to cancer remission. So it doesn't have to be death, even though we tend to use the word survival as if it was always looking at life and death. It's just a term that we use for time to something. So you can do a regression type analysis in a survival setting. And one technique is called Cox proportional hazards. Again, a lot of detail, you don't have to know this. The way you interpret the parameter estimates in survival, you do the same thing that you do for logistics, and you exponentiate the parameter estimates, and they will give you what are called hazard ratios, which are interpreted like odds ratios and risk ratios. So I'll give you a simple example. Suppose we look at all-cause mortality, so our outcome in this case is death, and this is analysis that I had from Framingham looking at a 10-year window, and what we have are age and sex. So we get a model. So this is a Cox proportional hazards regression. We have age and sex. If we exponentiate the two parameter estimates, the B's, we get those hazard ratios, which are on the right-hand side. And let's take the ratio for male sex. Over a 10-year period, men are about twice as likely to die than women, adjusting for age. The age parameter, there's about, another way to say this, each additional year of age is associated with an increase 1.1 times your risk of all-cause mortality. Or you can say each additional year of age increases your risk about 12%. If you want to do it that way, that's perfectly fine too, adjusting for sex. Okay? Now, some of you are asking a few questions about this. censoring. The censoring issue is a confusing one. And when you think of a study where you'd use survival analysis, often you start the study and your goal is to follow people for a long period of time because you're specifically interested in looking at time to something. And so what happens is a lot of people don't experience the event. They've been in your study and they might contribute a certain number of years and the study ends. You stop measuring and what you know is they didn't experience the event. So that person's time is actually censored. All you know is how long they were observed and didn't have the event. It also happens in these kinds of studies that because they're, by definition, long-term studies, people sometimes, drop out of the study. They might be in your study for 2 years, 3 years, 4 years, and they don't have an event over that time, but they contribute some time, and you want to count them in your study. You don't want to exclude them. So all you know is that they didn't have the outcome of interest for a couple of years, but then they dropped out, and you don't know where they stand right now. You can use the information that they've given you. Another complicating factor, as if it's not complicated enough, is that suppose your outcome is time to developing cardiovascular disease, and a person is in your study and you follow them for 3 years and then they die. This sounds weird to say, but they didn't have the opportunity to develop cardiovascular disease. So you want to count that time, and you have to censor their information. You use it, but you couldn't really get complete follow-up on them. And that's what's complicated about survival analysis. There's one last topic in here, and I just want to go over it very, very briefly because I want to leave a couple minutes for other questions that you might have, and it has to do with sample size. And all I want to say about this, there are a few slides in here that you can go through maybe if you have time yourself. Whenever you do a study, you should always figure out the sample size that you need. This is really important because when you do a study, you don't want to end up at the end of the study failing to find statistical significance to support what you're trying to do, or end up at the end and saying, this just wasn't precise enough for me to draw any conclusions. It actually gets into, on the extreme of it, ethical issues. And so that when you set up a study, you should always figure out what kind of analysis do I want to do and what's the sample that I need. And that should be something done at the very beginning and never at the end because it affects those type 1 and type 2 errors that you can make, and you don't want to find yourself in the position of not finding significance when you thought something really was going to have an effect, and then saying, well, gee, I just didn't have enough people. You've wasted your time and also the time of all the participants who were involved in your study. So I do apologize that I went this long. I wanted to go through the slides as best I could. But we do have a couple of minutes, 5 minutes, I guess, is left. If people have questions, I will try to answer them. There are a couple that are popping up here. For logistic regression, are those a combination of dependent and independent variables? Every time you have a regression analysis, whether it's linear, logistic, or survival, there's a dependent variable and independent variables. Dependent are your outcome variables. So for logistic, your dependent is the yes-no variable. For linear regression, your dependent is the continuous variable. Independent are whatever you want to use as your predictors. And they can be continuous, they can be dichotomous, they can be dummy variables. Why would you choose ANOVA over equality of means? They are actually similar approaches. So ANOVA, the way I distinguish them is the test of means is exactly 2 variables and you have a continuous outcome. ANOVA is, you could say 2 or more variables, that's fine, and in which case you wouldn't distinguish them. I just tend to say do ANOVA if you have 3 or more groups, but they are mathematically the same thing, so you could use either one. Is power 1 minus beta? Yes. And it's used to measure what? Power is the probability that you reject HO when it's false. You want that to be high. So whenever you set up a test, and it's related to this slide that's showing right now, you want to make sure you have a sample that's large enough so that if the null hypothesis is false, your test has a good chance of setting it up. Of detecting it. Okay, for when you're figuring out sample size determination, there are a number of inputs that you need, and the inputs, some of them are statistical, some of them are substantive. The statistical ones, to be quite honest with you, are relatively easy to figure out. You know, you want to use a 95% confidence interval, or you want to have 80% power. The effect that you're trying to detect, whether you want to detect a relative risk of 1.5 or 2 or something else, that depends on what you think is a meaningful effect from a clinical point of view. And so that's where we have to work collaboratively with our clinical partners to figure out what's a meaningful effect. Are there other questions that I've not answered? I'm getting notifications here all over the place that we're going to end. So where do we click to link these slides? Heather, can you come on to answer some of these questions? I don't know if you want to say anything about where people can find things. Okay, Heather's going to come on in just a moment. We'll just give her a second to get organized, and she can just give you some details on the logistics. Thank you all for your attention. I know this was probably painful to sit through all of this. A lot of detail. I'm sorry I stumbled over some of it. It was very quick for me too. There's Heather. I can't hear you. Oh, 1 second. Okay. She's giving me signals. She's going to be here in just a moment, so if you can hang on just a moment, she'll get to us. Again, please, I went into a lot of detail here. Big picture. There is a review chapter that's indexed on the second slide of this webinar that you can go to for some more resources. It's a chapter that I put together, and it attempts to kind of walk through all of this in text form, and maybe you'll find that useful to set up a big picture.
Okay, can you hear me now?
I can. Can others hear? Can somebody give us a signal? Yep.
Awesome, fantastic. Sorry about that. Too many things. The PowerPoint presentation, if you go to the website where you actually logged on, there is a link underneath the title, which we had posted earlier. And I know for some computers, the file actually downloads to your computer, and then you have to go to another location and open it, and that's particularly true for Macs. We will have another link, which will be obvious once this session ends, and it will be the recorded session with Dr. Sullivan giving the presentation as well as the slides. So that will likely be right next to the PowerPoint link. If you have any questions or you have difficulty, you can send me an email. My email address is hward@nbphe.org.
And another question asked, I don't know if you can see this, Heather, will the link to the audio stay up until the exam?
It will stay up for quite some time. We don't anticipate removing the link until we have a new review session. So it will be up for quite some time. My email address again is hward@nbphe.org, and I will post it in the chat box as well for everyone to see.
Great. Well, thank you, Heather, for the organization, and again, thank you all, and good luck with your exam.
Thank you so much, Dr. Sullivan. Good luck, everyone.
All righty.
All right. Bye-bye.
Bye.